schedule with the time. So we'll start at 9. So next 10 minutes, if you're coming late, well, you won't hear this anyway, but you're not missing much because we're just doing welcoming remarks now. And then we'll continue as we planned it with the talk. So this is the CVPR tutorial on evaluating models beyond the textbook, out of distribution and without labels. I'm Ludwig Schmidt, and I'm a co-organizer of this tutorial together with Weijian, Aditi, and Liang. Cool, it's super exciting to be back in person and being at a large conference. So let's get started. I don't think this is news to anyone by now. Over the past decade, there has been a ton of progress in machine learning, especially in computer vision, many exciting research advancements. And today we look at one of the key elements that enabled all of this progress. And this is rigorous evaluation. I'm sure everyone has seen a plot like this before. This is progress on ImageNet over the past 10 years. And ImageNet, I think, is a really, really good example of how important it is that we have rigorous evaluation practices in the field. Because initially, when the data set came out in 2010 and 2011, people didn't really believe in convolutional neural networks, and the error rates were very, very high. People thought this also is a very difficult problem. And then in 2012, the breakthrough paper from Jeff Hinton's group at Toronto came out, and they just did much, much better on this very challenging data set than everyone else. People sort of had to accept that neural networks are actually a really good idea. And then obviously everyone knows what came next. The computer vision community really switched over to neural networks as a very powerful method for a lot of different applications. And then specifically on ImageNet, over the following years, the accuracies got better and better. And by some level of performance measurement, now we are now at superhuman accuracies on ImageNet. And this is obviously not just ImageNet. I think the computer vision community specifically has been really, really good at setting up challenging data sets for evaluation, and then over many years making slow but steady progress that lead then to wider progress in a variety of data sets. So this is from the website Papers with Code, who keeps track of a lot of different evaluation data sets. I think this is MS Coco, this is Pascal VOC. It doesn't really matter. The main point is really just over time, the accuracy score.
Recording in progress.
And recording in progress, great, thank you. Let me quickly get this out of the way, so I can actually see what I'm saying. Got it, nope. Okay, good, yes. So over time, accuracies get better and better, and this is basically true across all of computer vision and machine learning more broadly. And this is all really great. So as we said, lots of exciting research progress over the past 10 years. And with this growing research success also come growing expectations for computer vision. People would now like to use all of these new tools, not just for writing research papers, but for building real applications in the real world. I think one of the prime examples that has got a lot of public attention are self-driving cars and various other applications in transportations like trucking and so on. Another big one obviously is healthcare, like various applications like medical chest ray analysis and so on. Robotics, online content moderations, and the list goes on and on and on. And it's great. I think this is these are many places where computer vision can have positive impact. But if we deploy computer vision in these challenging environments, it's also important that we can do so in a responsible way. And one key element there is that we have evaluation practices in place that guarantee reliable generalization in the real world. So now we don't need to know only, oh, is paper A better than paper B? But we want to know if we put the method in paper A or B out into the real world, how good is it going to be? And this leads to many new interesting questions for how to evaluate computer vision models. And this is going to be broadly the theme of this tutorial. And before we get to the main questions, let's just quickly recap how we do machine learning evaluations classically. I'm sure all of you have seen this before. This is what we teach in Machine Learning 101. We start out by collecting a big data set. Okay? And after we have our big data set, we split it randomly into 3 parts: a training set, a validation set, and a test set. So most of the data often goes into the training set. And then we do what we like doing in machine learning. We train models, tune the hyperparameters, and iterate many, many times, try out many different ideas, evaluate them on the validation set. And then the day before the CVPR deadline, we have our final model, and then at the very end, we take out our test set. At least that's the ideal story, right? Only once at the very end, we take out our test set, then we evaluate our final model on the test set, and we get some final accuracy out, like 83%. Okay, and this is great. Like if we follow this process, we have really rigorous guarantees of what this accuracy number actually means. Let's be a little bit more precise about this. What does it actually mean if we say we have 83% on a certain test set? And one nice way to illustrate this is with sort of a thought experiment. So what we get out of this test set evaluation is that the model will perform similarly on new data from the same source. In this thought experiment, there is some idealized data source that we can draw samples from. So we do this the first time to build our test set. Then we feed those images into our model, and we get our 83% accuracy out. Okay, so far so good. And what does this guarantee now? If we repeated the same experiment, we drew a new set of images from the same data source, following the same process, feed this again into the same neural network, then we'll get roughly the same accuracy back. Not exactly, because this is a random process, but up to statistical noise, we know that these two numbers will be close. But the big assumption here is that this only holds as a rigorous guarantee if we really repeat the exact same data generation process. Okay? So a little bit more formally, just to make sure we really nail this down. So that we make two assumptions when we use the holdout method. The first one is that there's a data distribution D over labeled examples XY. And then we have access, we don't have direct access to this distribution in the sense someone has given us the mathematical definition of this distribution. Instead, we have a set of samples drawn from this distribution, our test set, let's say n labeled examples drawn IID from this distribution. And then we can evaluate our model just by forming the sample average of the loss that the model achieves on the test set. And then if our test set is large enough, we know that this is going to be a good estimate of the population loss. So this is what we're actually after, this expectation, x, y, drawn from the distribution of the loss the model achieves on the distribution. Okay, this is all really nice, mathematically, lots of nice theory for this. But the big question is, what distribution should we evaluate on if we want to make sure that our model performs well in the real world? And none of this theory tells you about this a priori. And this is actually a really challenging question for a variety of reasons. And one is that a single test set often can't answer this question sufficiently. So if you have a single test set, you're only measuring performance on one specific data distribution. And in practice, what we often want is that the model should generalize reliably in a variety of different conditions. For instance, if we have a self-driving car, we want to make sure that it's not only driving well in expectation across the US, but it should drive well in every individual city that we deploy our self-driving car service on. The same is true for different weather conditions, time of day, and so on. And I'm not just making this up. This is obviously a very real challenge. And I think self-driving cars are often a nice way to illustrate this. So just to remind ourselves, the first time Waymo, one of the leaders in this space, launched a fully self-driving service in Arizona was in 2017, and it has taken them 5 years until they expanded this to now San Francisco. And this is the second city. So clearly challenging to generalize across different distributions here. And it's not just self-driving cars. The same happens in healthcare applications, for instance, where you want to generalize across different hospitals, across different medical devices, and so on. And each of these different test conditions requires its own test set. Good, so basically one lesson so far is we'll probably need a lot of different test sets if we want to evaluate our model in a reliable way. But then the next problem shows up is, okay, if we have all of this data we want to evaluate on, how do we do this? Naturally, data doesn't come with labels, so what should we do? So the first approach, if we don't have unlabeled data, obviously machine learning, we love data labeling, all of our methods are still quite label hungry. So the first thing you can do is you just label in new test data, but this comes with its own challenges. First of all, it's pretty expensive. By now, there are many companies like Snorkel, Scale, and Labelbox, which specialize just on the data labeling part of the machine learning pipeline. And it may also take a lot of time. Like if you sort of like set up a labeling pipeline every time you encounter new test data, this may prevent certain applications. And so the second big question for this tutorial is going to be, are there ways to evaluate models if you have only unlabeled test data? We obviously won't be able to do exactly the same things that we can do with labeled data, but it turns out that you can still make very interesting statements about the models you want to evaluate if you have only access to unlabeled test data from a new distribution. Okay, and these are going to be the two main questions for this tutorial today. It's at a high level divided into two parts. The first part is going to be, what test distribution should we evaluate our models on? And then, as I mentioned, the second part, what can we do if we don't even have labels for the data coming from the new test distributions? And sort of like, in order to illustrate this a little bit with a 2x2 plot here, you can think of this tutorial today as sort of like one dimension is in distribution versus out of distribution, and the other dimension is labeled versus unlabeled. So like the textbook regime that we all know about from ML 101 is in distribution data with labeled examples. And in part 1, Aditi and I are going to talk about out of distribution, but we still assume we have labeled data. And then in part 2, Liang and Weijian are going to remove the labeled assumptions and are going to look at out of distribution and unlabeled. And then let's just quickly look at the outline again to make sure we're all on the same page with time. So I'm only 1 minute over time right now. Aditi is going to take over right now with her talk on robustness. Then I'm going to come back with the second part and in the robustness part of this tutorial. Then we'll have a 30-minute coffee break. And then we'll have the part on unsupervised model evaluation. If you have questions, I guess no one has questions right now, but for these 3 main talks, we'll have about 10 minutes at the end of each talk for questions. And if you have something in the middle of the talk, obviously you're also welcome to just ask. Cool. So then I'll hand it over to Aditi.
All right, finally we get started. Thanks everyone for joining. My name is Aditi. I'm starting as a professor at CMU this coming fall, and I just finished my PhD from Stanford, and I'm currently at Berkeley. So this is my first time at CVPR and my first in-person conference in a long time. So it's really exciting, and thanks everyone for joining. So today I'll be talking about the robust optimization. There is an echo. Is it better? Okay, I'm just going to move on. So today I'll be talking about the robust optimization framework for evaluation. So for those of you who missed the morning remarks, because there was a little bit of a confusion over time, no worries, I'm going to briefly recap what's necessary. Okay, great. So first part of the tutorial today, we'll be focusing on what exactly is this framework and how does this, why do we care about this and how is this motivated in terms of the big question that we're thinking about, which is how do we evaluate machine learning systems in a way that captures what we expect from them when we deploy them in the real world. So what's the classical ML pipeline? As Ludwig mentioned, what we typically do in machine learning is we collect a data set of examples, and these come from some underlying distribution P. And then we split this typically into a train and a test set. We train on this training data, and we evaluate only on examples that come from the same distribution P as this distribution P that the training data was obtained from. Most benchmarks, as well as theory, study this setting where we care about held out test examples from the distribution P that the training data came from. But this is clearly insufficient if you think about real world performance, because what we care about is the wide range of examples that the model could encounter when it's deployed in the wild. And those examples are not going to be restricted to exactly being from the same distribution that the training data you used to train your model was from. So in this first part of the talk, we'll talk about how we can frame or how we can formalize this question of how do we care about a broad range of examples and how do we test models over this broad range of examples that it could encounter when we deploy. So in order to do that, let's get some inspiration from what are realistic examples that we could care about. Let's look at self-driving cars, which is a popular example because any mistake can be catastrophic and we really want to avoid making mistakes on new inputs. So if you think about driving in California, where it's going to look pretty sunny on most days, it's great. But I'm moving to across the country, and I'm going to have to deal with different weather conditions. And so self-driving car as well has to really deal with changes in weather which might not be predictable. And in particular, we don't want to only work well on that distribution that you trained on because the weather could change in ways you didn't know about. So what we want is we want self-driving cars to work reliably in all possible weather conditions. Only then we know that the system is ready to be deployed. As another example, let's look at pedestrian activity. So pedestrians could mostly be using a crosswalk, and this is probably what a large fraction of your training data would represent. But we want to also work well in cases where pedestrians may be jaywalking, or they may be skateboarders, and you don't know like how fast they're going to go. And where I come from in India, there might also be cows on the road, and you kind of want to deal and work well with all of these cases, and not just like the distribution in your training. So as another example, we want to work reliably in all kinds of pedestrian activity, including things that we might not have anticipated or collected data carefully for. And then if you look at healthcare again, like, we might get some training data from a certain region or like a certain slice of the demographic, but things change. For example, there might be a pandemic and that might change the kind of patients you see. You want to work well across different regions, like ages of people change, there are all these changes, and you want to work well in all these locations and conditions. And as a final example, if you look at facial recognition systems, it seems like they work quite well on average, but there's been a lot of literature to show that they don't work well on certain demographics. And for many years, there's been an issue, and even recently we see such errors. And so this reminds us that, again, we don't care just about the average case performance or like performance on the demographics that are represented in that particular distribution you created your benchmark on, but we want to work well across all subpopulations. Another interesting thing that comes up when we think about deploying systems is that if you look at applications like content filtering or facial recognition or spam filtering, these are all cases where certain bad actors have an incentive to try to break your system. For example, you want to post some spam and you have an ML-based system. If you can change a few words here and there and like basically get your content across, that's great. And people are going to try to do that. And especially, they're not going to restrict themselves to the kind of distribution that you collected your training data on. And so we want to make sure that we work well across all adversaries who might be trying to break the system. So with those few examples, let's just take a step back, think about like, what are all these things that we care about? So we want to work on all conditions, all subpopulations, all adversaries, and so on. So one thing that strikes out is that, well, maybe we might not ever be able to collect test distributions that reflect each of these different things we care about. So is there something that we can do more efficiently? And one natural instinct, especially like, for me coming from a more TCS background, it felt very natural to think about, well, I should just get good performance in the worst case. And if I could get good performance in the worst case, then I have already covered all these different cases that could happen. And that's kind of the best thing I could hope for. So this seems like a pretty natural kind of gold standard evaluation where we look at how well the system does under worst case. And so this is naturally going to encompass all like the other variety of cases that you could have in practice. So that's kind of the nutshell of like the core idea of like this worst case evaluation framework or the robust optimization framework. So as a reminder, if there's any pressing questions in person, please feel free to like raise your hand and ask, and Ludwig will be monitoring the Zoom chat for any questions that come up, but we can also take questions at the end. Okay, so here's a robust ML formulation. So classical ML, like as everyone knows, is you have a bunch of training data from some distribution P. And the test metric that we usually think about is how well your model does on expectation over new examples from the same distribution P. In this robust optimization setting, we still have the same training data. But like we said earlier, instead of just thinking about how well this model does on that one particular test distribution P, we really want to think about a variety of different test distributions and look at the worst case performance across them. So you might have any distribution Q within a set of distributions that we define as C of P. So we define a wide family of distributions that the model could encounter. And to make our life easy, instead of checking each of those things, we just want to work well on the worst case. And this automatically tells us that we work well on everything within this broad range C of P. So visually to think about, you have this training distribution P, and then you define a set of perturbations across this training distribution. So you can have a bunch of different variations of this distribution, and that is all encompassed under the C of P. And we want to get good performance in the worst case across all possible distributions within this family. So that's the idea of robust optimization, which makes a lot of sense because we want to work well across a wide range of distributions. So let's just define that and look at performance in the worst case. So just to see how this compares to the other kind of settings that that are quite popular. So in many cases, we might think about looking at a distribution or evaluating on a distribution different from the training distribution. So one common situation is called transfer learning. So where you have labeled samples from one distribution, you want to work well on another distribution, but you also have labeled samples from the other distribution. Whereas in the robust optimization setting, we do not know anything about the exact distribution of tests that we care about. Instead, we care about the worst case across a family. In the domain adaptation setting, we get labeled samples, of course, from the training distribution, and there are some unlabeled samples from this other distribution that we call Q, that is the test distribution. So we still get some information about the test distribution we think, and there is one test distribution we care about, but we only get unlabeled data from that. And a setting that is more common to like what we are looking at this talk is where we do not know exactly the test distribution, and that is domain generalization. But there we assume access to a bunch of different distributions that implicitly define kind of what is this family. So there, what you do is you assume that there are several distributions that you see, and you're going to generalize to a different new distribution across the same family that all these distributions came from. So the thing in domain generalization is that the training distribution implicitly defines this family that we care about, whereas in the robust optimization, we don't assume anything about your training set, like we just have one distribution, and we want to work well across a bunch of different things, which kind of captures a realistic setting that we are going to get training data, we're going to train on it, but we want it to work well across a bunch of different things. So with that, let me jump right into some concrete instantiations of this robust optimization framework that have been typically looked at within the robustness community. The first is adversarial examples. So perhaps a lot of you are familiar, but adversarial examples are quite the striking phenomenon where we see such mistakes that happen. So here is a stop sign that a good model would correctly classify as a stop sign. But you can make some really small changes and add these stickers. And the stickers don't change the way you or I think about the stop sign, but the model would now completely change its predictions and call it a speed limit sign. So you can see how this is very dangerous because, well, in the wild, there are going to be all sorts of stop signs. And if a model gets confused, then like, how do we trust these systems? So the more canonical example is as follows. So this is an image of a lakeshore. And if you take any good ImageNet classifier today, it would correctly classify it as a lakeshore. But I can make really small changes to this image to get this new image on the right, which very much looks like the same image on the left, except that each pixel is changed by a small amount. And this is imperceptible. But now a model is going to call it a completely different class of laptop. This is pretty striking. And again, like, how do we trust these systems and what do these models learn if something as simple as like a few pixel changes can completely change the way the model is perceiving this input? And for this reason, this question received a lot of attention within the community. And it's also just like intellectually very curious because like, why is this image that looks absolutely the same considered so different by the model? So this issue received kind of a lot of attention, and there's this general goal of trying to defend against such small changes. And so the informal goal here is we want to defend against attacks that perturb inputs. So usually we'd have a test input that we want to do well on. But instead of just looking at that test input now, what we do is we define a set of perturbations that we denote by this B of X. So there are perturbations around this test input X. And we allow an adversary to perturb this input to any point within this set. And we want to make sure that the model gets this right. That's the goal in adversarial examples. And depending on how we define this set of perturbations, we can get different kinds of robustness. For example, this could be like this imperceptible set of perturbations that we had before, where we can formally write down the ball as follows, where every pixel is changed by a small amount. All these set of perturbations could have things like stickers, and we get the stop sign example from before. And we could consider various kinds of perturbations, like there could be rotations, translations, or changing the background, and so on, lighting conditions, etc. So the idea in adversarial examples is we take an input and then we define a set of small variations to the input that are basically semantics preserving. So there are small changes that don't change the label. And we want to make sure that the model does well on all these perturbations. And the way we measure that is like allowing an adversary to find something within the set of perturbations and see whether the model can still get it right. And this is a convenient way of, rather than evaluating each perturbation, we just want to look at the worst case perturbation. So just a quick nuance on like how it connects to the robust optimization. So in this adversarial examples, you have an input and then you define a set of perturbations and we want to do well. And what I presented earlier as a robust optimization framework is you have a distribution, training distribution, and we have a family of distributions around it. So there's you go from the instance level to the distribution level. And you can actually mathematically connect these two and show that they're equivalent for LP balls. That is when this set B of X is like an L infinity ball or an L2 ball via something called the Weijian distances. But morally, you can think of perturbing instances as basically inducing some kind of perturbation on the distributions. So this is basically part of the framework of robust optimization, where we are trying to evaluate on a whole family of distributions at once. So that's about the definition of adversarial examples. And it makes sense as something that we want systems to have. Of course, it's not the end all, but it feels like a starting condition is like, well, at least on semantic preserving small changes, the model should retain its input, retain its predictions. But one thing that kind of strikes us when you think about worst case evaluation is this really tractable? Like, how do we even measure performance in the worst case? So like I said, adversarial examples has been quite popular for a long time, and there's been a lot of work in this area. So what does that look like? So here is a sampling of papers like from the early days. So in 2013 was when this notion or like this existence of adversarial examples was shown. And very quickly, there was an idea of a defense that was proposed. And so the reason that this problem was challenging was not really that there were no ideas on how to try to defend. So there were a bunch of different ideas that were proposed. But what happened is very quickly, it was seen that all these defenses that were proposed were actually not robust and you could break them. So there's a little bit of a problem where there was an idea that was proposed, but then there was a follow-up paper that broke this. And it's not just like one example. There are other examples as well. For example, there's a blog post that claimed on July 12th that we don't have to worry about adversarial examples, because they said that if you had multiple views or like different depths and so on, like these things disappear. And just 5 days later, this is again shown to be broken. And in 2018, there was this kind of striking phenomenon of this, where like there were 7 papers that were published at iClear that were all broken before the next deadline of ICML. So there's a little bit of this problem that kind of clearly, strikingly shows that, well, adversarial examples are like kind of nice. You can write down this worst case thing, but well, how do you actually evaluate it? And that seems to be quite challenging. So one thing is that, evaluation of robustness is indeed quite challenging. So what could you do? Well, there are some natural kind of better practices that we could try to use, which is, consider adaptive attacks, for example. So don't just rely on like whatever people have tried to break the systems, really just go hard and try to break your new idea. So consider ways of modifying the way you find these examples to like really test your idea, and then perform some sanity checks and so on. So there's been like over time across the community, there's been a better evaluation standard to avoid at least the issue that you're just going to get immediately broken in a few months. And there are also ways to like tune your hyperparameters and so on to get better attacks. So in general, we are now at a slightly better space and like trying to evaluate. But all of these things actually still don't give you a guarantee. Like, are we actually still measuring the worst case? And if you recall, like the whole, the motivation for robust optimization is that we want to really get a guarantee, because it's not sufficient to just test out a bunch of things and like say that our system is good. We want to get some kind of a worst case guarantee so we can really just trust that the system's going to work. So is there something we could do there? So fortunately, there is something we can try to do in terms of getting guarantees as well. Okay, sorry, I see a question on the chat. Let me. Yeah, so to respond to Elena's question, so we only allow really small perturbations on natural inputs. And so you don't really cross the boundaries. So that's why, like, at least on natural inputs with small perturbations, you can get a model that retains its predictions. So to like repeat the question for people around is, are we making the, like, is it a problem that we want the model to give the same answer on perturbations? Because then you're going to force yourself to just be the constant classifier. And I guess what I'm responding is that if we only care about really small changes that clearly preserve the label, then we can get a function that actually is going to get the right answer on these perturbations. And in other words, you can, there is an option to say, I don't know, on like meaningless inputs, but those are not things that we actually care about when we evaluate these things. Okay, so going back, so what we are trying to see if we can get guarantees on performance for these worst case adversarial examples, because at the end of the day, the formulation allows us to really get a sense of guarantee, and is that really tractable with the kind of models that we have today? So what makes this question really challenging? So why is it hard to evaluate? So you have an input, and let's just illustrate this for a binary classification. So it goes through a network, and you get a score for each of the classes. And depending on whichever score is higher, you assign that class to the as the prediction. So this is typically how we think of what comes out of the model. Now, what happens when you perturb the input? So when you perturb the input, you can try to see what happens to the corresponding scores. And because your input goes through a neural network, which has many layers and non-linearities, what comes out could be this really complex non-convex object that is the scores corresponding to the perturbations. So if we were to reason about this like non-convex complicated object, we run into problems because there are all these corners that you might miss out. You don't really know if there is a point that actually a model gets wrong. So one way to get a certified evaluation is the following idea. So rather than looking at this exact set of non-convex perturbations that correspond, or the non-convex set that corresponds to your perturbations, let's make our life easier and instead look at this wider like convex object that encompasses, or that has everything that actually comes from perturbations. And if we show that this entire set is actually correct, or like the scores obey the property that you want, then we know by construction that everything inside, which actually corresponds to perturbations, also has that guarantee. This is kind of the key idea, which is that we construct a convex relaxation, which makes optimization easier. And by construction, we get a guarantee that if this whole convex object obeys some property, then everything inside it as well. And so this allows us to get some kind of a guarantee on robustness. So there are nuances as to like, how do we make sure this relaxation is tight enough so that you don't become vacuous? So one relaxation is just like the whole space, and that's not useful. So we want to construct it in a way that we get something that's meaningful, but it's also easy to search within this convex object. And you can use this whole machinery of convex optimization. And so that's this whole field of certified evaluation, where we can get some kind of guarantees via convex relaxations on actual worst case performance of these systems. So all hope is not lost. Yes, it is challenging, but we are able to get guarantees on how well these networks perform on small perturbations to inputs. So in that way, like, there might be a cat and mouse game that is involved with like worst case evaluation, but just this formulation and using convex optimization allows us to eventually get guarantees on performance. And it's great for like reliability, because now we don't have to worry about things being broken in the future. And with that, I'll switch gears to a different kind of robustness within the same family of worst case optimization called subpopulation robustness. So there are many settings in the real world where ML ends up discriminating against certain groups. So there's this really popular example on facial recognition systems that show that if you look at, for example, the errors on darker females, it's like much higher than the error, oops, there's a typo here, on light males. So there are many such examples where there are different subpopulations or demographics, and your model doesn't work well on all of them. And in particular, on the minority groups, you work quite badly. But this is not reflected in just the benchmark or like the average accuracy, because it forms a very small portion. And so that's what we want to try to rectify by looking at a broader set of evaluation distributions. And this is really especially a problem in the presence of spurious correlations. So there are many patterns that might exist in your data set, and your model is going to pick up all of them. And so if you're not careful while evaluating, you're going to, like, your model is going to miss out on actually learning the true thing. There's another example of spurious correlations, which are these misleading heuristics that I find quite striking. Is, if you want to use machine learning to help you in healthcare. For example, you look at chest x-rays and you try to decide if this has a collapsed lung or not. You can use ML, you can download a data set, train a model, and would correctly say that this has a collapsed lung. But turns out there is actually a spurious correlation here. And so if you see carefully, there is a tube which corresponds to the treatment. So the way this data set was collected is that every person who was flagged to have a collapsed lung also received a treatment which showed in the X-ray. And the model was really just looking for the presence of this treatment to make its predictions. As a consequence, when you had an untreated patient, the model just did not detect this collapsed lung. And this is a really big problem because this is exactly what we want the model to be used for, and like it clearly failed in what it was intended for. And there are many such examples, even in the more common benchmark. For example, it turns out that watermarks are highly correlated with the category of a horse. And so if you just remove the watermark on Pascal VOC, now suddenly the predictions change. And the common examples, of course, the background is often correlated with the label. And so models do rely on the background to make these predictions. So there are all these spurious correlations, which again, you don't really think your model, or like you never know if your model picks up on that if you just evaluate on the test set, because the test set is from the same distribution and encodes the same correlations. But when you deploy it, for example, in like that chest drain example, of course, you're going to find examples where the correlation breaks, and then we want to make sure that the system's not broken. So what do we do in these cases? The subpopulation robustness is a nice way to think about evaluating robustness to these situations. So we have this distribution P, but it's really not this homogeneous thing. So there are subpopulations, or there are different categories, or that we can partition this distribution P into. So there might be these groups, for example. And so we might have training data from P, but they actually come from all these different groups. And instead of evaluating on just the same distribution P, that is basically some weightage of these different groups, what we want is to make sure that the model does well on each group individually. So you sample points from each group, and you want to make sure that the worst case performance across all different groups is still good, which means that the model is not doing well just on the majority group, but is really getting all these partitions of your training data, or like your training distribution correct. So these could be subpopulations, which means that just because the data set has like a larger fraction of light males, you still want to do well on like the smaller fraction of dark females, for example. And this is also commonly referred to as group distributionally robust optimization, for like the obvious notion that there are these groups that we care about and we want good performance in the worst case. And so how does this connect to spurious correlations? So one way we can try to think about spurious correlations is that we can, again, like there are some parts of a data set that have this correlation, but there are some parts that don't. And so if we partition our data set into groups that have and do not have this correlation, we can say that we want to work well even when the correlation doesn't hold. And that kind of means that you're not really relying on just the spurious correlation. So the simple case, you might have a label and like a spurious attribute. And so we divide the data set into 4 different groups depending on the label and the attribute. So for example, if you have like different backgrounds, so like you might have, say, a water bird in water, and that's in one group. You have a water bird in land, and that's in another group. And so if we really think about evaluating on all these different partitions separately, then we're not just focusing on spurious correlation and allowing the model to use it. So we can divide the data set into groups where they obey and do not obey this correlation. And typically, like since the correlation holds on most points, so you have these majority points where the correlation holds, but we also care about evaluation on the minorities. And again, the usual group robustness formulation would make sure that we evaluate even on points where the correlation doesn't hold, as a way to check that the model is not relying on something spurious. Because when we deploy, like majority of the points might actually not have this spurious correlation. And a natural follow-up question is like, well, this is all great if we knew this set of groups, and then we can divide our data set accordingly, evaluate accordingly, and so on. But what do we do if we never knew anything about all these groups or what the partitions in your data set actually are? So one idea that is quite common and that people have thought about is, well, we just want to work well on all possible subgroups. So we never know, like, there might be some latent way that connects a different set, like some set of individuals together. And we want to protect against all those possible ways that we might not have thought about. So what we want to do is any collection of data points that is reasonably large size, we want to make sure that we do well on them. And so what we do here is, like in this robust optimization framework, instead of setting the set C of P to just have particular groups, we just define it now to instead have all possible groupings of your data that have size at least some alpha. So what this turns out to be is called the conditional value at risk DRO, where basically we take the alpha fraction of points that have the highest loss and say that that set has to actually be small. So what we don't want is a case where there's a really long tail where like most points are fine, but there's some subset that has a really high loss. We want to protect against this because, well, the long tail could actually correspond to some latent group that we didn't know about. So instead, we want the losses to look like they don't have a long tail. And so the way we measure that is we look at the last fraction of the points and make sure that they do not have a very high loss. So that's what you could do if you just didn't know anything about the groups. And so this is a natural strategy to try to avoid the situation that there is some latent group that that has a very high loss. So here are some examples of data sets that they've looked at in these different settings. So a very common synthetic setting is colored MNIST, where we create a spurious correlation between the digits and the colors. So as you can see, like maybe the odd digits are one color and even digits are another color. We want to check whether the model can not just use color to make its predictions. Another popular synthetic benchmark is water birds, where we take images of birds and images of backgrounds and create a particular correlation where most examples of water birds are in water, land birds in land, and so on. And we test whether the model does well even when this correlation is broken, for example, a water bird in land here. So there might also be more real world situations with known spurious correlations. For example, the Celebi data set that perhaps a lot of you are familiar with has many different attributes, and there are a lot of correlations that are kind of interesting to look at. For example, gender is correlated with hair color. So it turns out that there are very few male celebrities who are blonde. And so if you're blonde, you're typically female, and there's this correlation. And then there's, of course, a correlation between earrings and lipsticks. If you're having earrings, it's very likely that you have a lipstick and so on. And so you can try to see whether your model is able to work well, even when there are these correlations present. And the other data set is the CheckSpurt device that I spoke about earlier, where there is this device that is correlated with the presence of a disease, and you want to see whether your model can still work on recovering the true underlying way to detect the disease and not relying on just the treatment. And there are also other real world settings, which people have considered there are new data sets. But the caveat here is that they're in the unknown setting. So we don't know the group, so we don't know the correlations, and we want to check whether we can still do well. One example is functional map of the world, which is satellite imagery. And so you have data sets from different demographics and different times, and you want to generalize across different regions. And again, so it turns out that if you just did normal training, the performance deteriorates quite on certain regions. And this is, of course, because there are some correlations that might hold in certain demographics, but not others. But there's no way, we don't know exactly what those are. Another example is like identifying the type of crop. And that also shows a similar observation where depending on the weightage in your training set, you pick up different things from different regions, but we don't really know what exactly those correlations are. And so this is a good setting for testing models. In the setting where we don't know what the groups are, we still want to do well. So to quickly summarize this robust optimization framework that we have, so we start off with adversarial examples, which are these instance level perturbations. So we have an input, we define a set of semantic preserving or small changes, and we want to make sure the model does well on the worst case perturbation. We might have subpopulations as well. So this is like a little bit more at the population level, and we just break down this population into different groups. And we don't want to do well on just like one group or the majority group or like that fraction in your training distribution. You want to do well on all of them individually. And this is typically used to measure fairness, or spurious correlations can also be modeled under this framework. And then there's the other notion that we do not know the subpopulations. And so we really want to focus on the tails to make sure that there is really no set of points that are large enough that works well, that the model does badly on, sorry. So I'm running a little short on time, so I'll very briefly speak about the next two parts, which are, so I spoke a lot about this evaluation, but we can talk about how well do models actually work and show you some numbers. And then in a few minutes, Ludwig will start. So the main takeaway is that we have this really nice formulation for evaluating, but when we actually apply that in evaluate systems, we find that if we just did the normal ERM that, that most of CVPR, for example, does, we find out that like the performance is just really bad. So the worst case error is almost 100% in all these different ways of evaluating. And so that led people to think about how do we train models to allow for this kind of robustness. So, don't want to spend too much time, but the main idea is that, well, we just apply the same. So in ERM, we care about performance on the test distribution. And so what we do is we just measure we minimize the empirical version, right? So we just take average error over your training set and then you minimize it. In the robust training, well, we care about worst case performance across the set. So let's just minimize that at training. So that's basically what the robust training looks like, is just to minimize performance on the worst case versions of your training data and hope that it generalizes to the test set. And it turns out that this formulation is nice because you can actually get various optimization and statistical guarantees, just like you get from classical ML for a variety of different settings. That is, you can prove in certain cases that minimizing on the training, these worst case things actually minimizes on the test set. I'll skip over these and just show some numbers. So like I said, if you just did evaluation, things look really bad. So standard training, if you just did that, you like, for example, your robust error is 100, even though your standard error is really low. So you can do this robust training or adversarial training, which is basically minimizing on the training set. The robust error improves, but it's not great. And you see that the standard error also gets worse. And many variations have also been proposed. And over time, we've not really seen a better situation. So the robust error is still pretty high, and the standard error also increases. So these are two problems that come up with doing this robust framework, which is that you don't even get as much robustness, and the standard model's error is the standard error is high. So we compromise on average performance when we focus on the worst case performance. For adversarial examples, you can show that this is actually because the problem is statistically harder, which means that maybe we need more data to solve the problem. And there's also this issue that robust learning can interfere with the inductive bias of these deep networks. And so that actually, that kind of explains why the standard error goes up. So you have these two effects. One is the robust error is just a harder metric. You need more data. And this trade-off can happen because, well, if you focus on something, then the network's inductive bias kind of ends up making it generalize less, unlike the average case. And so for both of these, we have like a solution that provides partial gains, which is robust self-training, where you use a lot of unlabeled data to help with the statistical issue, and you regularize it in a particular way to deal with the standard error. Yes.
Could you explain it further how robust learning?
Yeah, so one thing that can happen is, like, so let's say there's a very simple pattern in your data set and your model kind of can pick that up and generalize well if you just care about average. But now if you care about robustness, you're forcing your model to pick up more complex patterns because you want it to be like locally stable or something. And that can just be a much harder problem. And so that could cause it to generalize worse. For example, if you force a network to pick up on local features, you can see that it compromises on the general global patterns. And so that's like one thing that could happen. So it's just like, yeah, if you look at like linear interpolation, that can work really badly if you want like local stability. So that's an intuition. So we see some gains. So like if you just use self-training with like appropriate regularization and more unlabeled data, so you improve your robust error a little bit and also your standard error. But of course, this is kind of far from what we expect as optimal. So even if we optimize exactly what we care about and use a lot more data, it turns out this is quite challenging to solve. In the interest of time, I'm just going to briefly mention that we see this interesting observation when we do, so the other kind of robustness that I spoke about was with groups or subpopulations. And so if we optimize for the robust optimization variant here, what we see is that with really large models, you don't really get good performance when you look at the robust error shown in blue. So you should actually use much smaller models to see some improvement with this robust optimization. So if you see here in both these curves, the performance of the blue, which is a robust error, is much better on smaller models than larger models. So again, there's this like weird trade-off. So this again connects a little bit to the inductive bias of how, like if you have too many parameters, just upweighting groups or changing the weightage that you pay to different groups doesn't really solve the problem, because the network can still find ways to cheat and fit everything. Whereas if you regularize it, things are great. But if you regularize too much, you start compromising on the average performance again. So there's again this kind of trade-off when we try to get robustness. Okay. And finally, if you don't have groups, the situation is even worse. So you can be overly conservative. So if you look at CVAR DRO versus the group DRO, that is, if you knew the groups, if you didn't know the groups and you had these, if you did the unknown version, your standard error increases much higher and the robustness is also not great. This is kind of intuitive that even if you knew the groups, it's hard to get good robustness without compromising on average performance. And it gets much worse if you don't know the groups. So to summarize, so robust optimization is this really nice unifying formalism that captures the worst case evaluations we might hope in practice, because as we saw in many real world settings, we never know the exact distribution we care about. And so it makes sense that we want to think about worst case. This is great, but we have challenges. So one is evaluation itself can be challenging computationally with the kind of models that we have today. As we saw in the case of adversarial examples, you could have this cat and mouse game. So evaluation is tricky, though we could hope to get some guarantees. And finally, the training itself can have problems because it's statistically harder, you need more data, and it could interfere with inductive bias in some ways. It's non-trivial to just incorporate robustness into your training and just give it into your current pipelines. We really have to think more carefully about regularization and parameter count and so on. And of course, the next question is, we have defined this set C of P, it's all great, but like, what if we didn't define this correctly? What if, does it do anything outside the set? And that's kind of what Ludwig's going to talk about, is like, well, we can, have this formalism, we care about certain things, but does it lead to other changes meaningfully outside the set as well or not? So with that, I'll pause for questions. I can take questions while Ludwig sets up, I guess. Yeah, the mic is working, yeah.
So it's that question of the like So it seems like a lot of these like papers that you're like, oh, we can use the great things, especially when it comes to like pixel perturbations. To me, sometimes seems like you're solving a problem that doesn't really happen really well. For instance, fingers on the stop sign seems like that could be something like that. Whereas these like small perturbations of pixels where it looks similar would only sort of happen in a like malicious adversarial attack, which I don't know how often that's seen in the today. So I guess what's your thought on like how to deal with that? So, how do we solve like a real problem?
Right. So I think there are like two aspects here. One is just the techniques and the foundations and like the hope that they transfer. So like, for example, if you can define various kinds of perturbation sets, and the tools that you have to defend are like pretty much the same. And so the question of actually designing the right kind of perturbations is like less of to me, like a less of an ML question and more like an application, like security question. And so the hope is that we construct settings that we think are like general and simple enough that we can make progress, and like hopefully that that can be a complement, like actually designing some of these things carefully. So that said, like given that how it's so much more challenging, and like I guess when we started the question initially, it wasn't clear whether it's like a hard enough problem or like, can we just solve it and move on? And so given that it's really hard, I guess now there's a little bit more focus on like, maybe we should, this is just impossible to solve. And we, in the meantime, need to like think of more tractable things that like might be more realistic. But I still think that the gold standard is to be able to do this for anything, because at the end of the day, perturbations are also something we do care about, like maybe not the most important, but it's like it feels like a necessary case for like complete reliability. Yeah. Yeah.
Just a couple of questions. One thing was on adversarial perturbations. Maximum perturbations have the effect of just smoothing the distribution. So, what additional impact do you see beyond
yeah, I guess like, Ludwig's going to show a little bit, some plots that talk about it. But I guess, yeah, in some sense, it's a hope that by forcing a model in high dimensions, of course, the intuition is a little bit different. So for example, like the fact that these perturbations exist tell that your model picks up on certain high frequency signal that we just ignore as like in our visual system, because you change those small things and like you change the high frequency components.
Decision boundaries are very complex. That's what it shows.
Exactly. Yeah, no. So I think actually it's like the reverse. The model learns something that's like pretty smooth, and we are trying to make them more complex to like capture like local stability. Because if you just use all the features that you had, then you might just get something that's very simple, but like it doesn't have the kind of complex structure that like we have for like what really a digit one means or a two means. So I think it actually makes it like more complicated. And the hope is that by doing that, you force your model to learn more meaningful features, and so that leads to better generalization in other contexts, which doesn't always hold, but sometimes does.
Thanks for that. Another question. Have you tried things like, for MST, re-listening MST and so on? And I would suspect that this might be some scheduling, right? But then you use fixed scheduling.
Yeah, I think people have tried a bunch of different like scheduling of that, but like there are some fundamental issues with like for example, this like statistical trade-offs and just the average versus worst case. You can prove in very simple settings as well they exist. So those are things that we do not hope will just go away with better scheduling or better training. But there are like some gains that do come by scheduling. For example, if you schedule epsilon, especially, it's known to be like very important to improving robustness. So those do provide some gains, but those are like more like training heuristics, which don't address like there are also fundamental things, so it won't completely bridge the gap. Yeah. Maybe I'll take the rest of the questions during coffee break. Okay.
Maybe you want to answer that one.
Let me reply to that on text.
Okay.
Yeah. All right. Thanks, everyone.
At a high level, over the past few years, researchers have proposed a lot of different robustness notions, ways to test neural networks. And there's a big question coming out of all of this: how do these different robustness notions fit together? So, like, okay, neural networks fail in a variety of ways. Are we making progress towards models that are broadly more robust, not just to one of these different kinds of robustness issues, but ideally many of them? And this is going to be, or these are going to be the two main questions for this part of the tutorial. So in the first one, we'll use data as test data to evaluate robustness broadly against all of these different distribution shifts. And then in the second part of the talk, so the first part is going to be the focus because this is the evaluation tutorial after all. In the second part of the talk, I'll also want to touch a little bit on one very promising direction currently for enhancing the robustness of models, especially to natural distribution shift. Okay, cool. So let's get started with the first part. And this is going to be based on the following paper: Measuring Robustness to Natural Distribution Shifts in Image Classification, that collaborators at Berkeley and I wrote towards the end of my postdoc there. And basically what we did was, in the context of ImageNet, just evaluate everything that was out there. So like the core like experimental data that we collected is the following matrix here. So 2 dimensions. On the y-axis, we have different models. So really, we just collected all of the pre-trained checkpoints we could find, and in the end had about 200 models in our test bed. So every row in this matrix corresponds to one model that researchers had proposed. And then on the x-axis here, we have all the different test conditions that researchers had proposed in the community. And in total, we collected over 200 different test conditions. To give you a bit of a sense of what's in our test bed, let's first look at the model dimension. So at a high level, you can divide the models in our test bed into 3 different categories. We have one kind of model that we call standard models. These are ImageNet models that we are trained just with the goal of increasing ImageNet accuracy. So starting from AlexNet, all of the standard ImageNet models like DenseNets, VGG, ResNets, and so on. So they serve as a very useful baseline. And the second kind of model that we evaluated are what we call robust models. So these are models trained with some robustness intervention in order to be more robust to one kind of distribution shift. And then the third kind of model that's important in this experiment are models trained on more data. So the first 2 bullet points of models are trained just on ImageNet, but it turns out that models trained on additional training data have very interesting robustness properties, and we also collected some of those. Okay, so this is the model dimension of the testbed, and then on the x-axis, the distribution shifts. Again, we collected what's out there, so all the ImageNet variations that people collected, like ImageNet v2, ObjectNet, ImageNet R, and so on. Then we also have various kinds of adversarial attacks, L2 norm, L infinity norm, different strengths of these perturbations in the testbed, image corruptions, and so on. Okay, so there's a lot in this matrix, right? So every cell in this matrix corresponds to evaluating one model on one test set. And in order to structure this a little bit, for the talk today, we are going to classify these different robustness notions along two axes. The first axis is adversarial versus benign. And what I mean by that is, does the distribution shift, does the input perturbation depend on the specific model that we are currently evaluating? Okay, like adversarial examples would be a prime example of an adversarial robustness notion here, because the perturbation depends a lot on the current model. And then something like just adding Gaussian noise would be a benign perturbation, because the Gaussian noise doesn't care about what the model is. So this is one axis, adversarial versus benign. And then the second axis is what we call synthetic versus natural. So the idea is the following here. Quite a few of these ImageNet distribution shifts that people work with don't actually correspond to real data. Like often people start out with the ImageNet test set or another test set, and then they apply corruptions purely in the computer, like adding Gaussian noise, adding a motion blur, and so on. And this is very useful as a starting point, because it's much easier to apply these perturbations in a computer. We don't have to go out and collect new data. So it's a good starting point for studying robustness. But the catch is that it's actually, as you said, in the end, not real data. So the second kind of distribution shift along this axis that we look at is what we call natural distribution shifts. The idea is here, these are real images as they occur in the real world. Someone recorded them with a camera and then put them into a test set, and there are no additional perturbations on top of the image recording process. Okay, so these are the two dimensions we'll divide our big evaluation grid into. And before we dive into the results, let's quickly think about how we are actually going to measure robustness. Okay. Since we have this large number of models in our testbed, as we said, over 200 different models, they all have different in-distribution accuracies. And it's important to think about this in detail, because in-distribution accuracy is going to act as a confounder in our experiments. To illustrate this with a small example here, let's say we have two models, model A and model B. And in the in-distribution test set, model A gets 80%, model B gets 90%. Model B already has a in-distribution accuracy. And now if we go to an out-of-distribution test set, let's say model A sees a drop from 80 to 75, and model B sees a drop from 90 to 77. Okay, so which of the two models is more robust? If you just want to deploy the best possible model, then you should clearly still deploy model B, because it still has higher accuracy out of distribution. But the interesting thing here is, from a robustness perspective, that model A has a substantially smaller drop. Model A drops only 5% from this distribution shift, and model B drops more, it drops 13 percentage points. And if we want to understand robustness, we should understand what makes model A special here compared to model B, so that it's more reliable under this distribution shift, in the sense that it sees a lot smaller accuracy drop. Okay, so this is the idea. Let's look at this in the context of a specific distribution shift to get started. It doesn't matter what's on the y-axis right now exactly. We'll put ImageNet v2 there, just to have something concrete. But overall, the picture is going to look similar in many of the distribution shifts we look at. So x-axis, we'll put image, y-axis, accuracy under distribution shift. So two-dimensional plot. And then the dashed line here, y equals x. This is where you would end up if you don't have an accuracy change on distribution shift. And then for all of these distribution shifts, the point is that the models do worse. So the blue points, which are the models, will be below the y equals x line. And as a starting point here, all of these blue points I put on this plot are what we call the standard models. So these are models just trained to do well on ImageNet. Start going from AlexNet over VGG, ResNet, DenseNet, everything we could find, up to the best model that we found at the time, which was an efficient variant. Okay, and one thing that's quite striking is that all of these models are on a pretty clean linear trend. There's an interesting question why that is. For now, we'll just take it as a given, because it really happens for all of the models we could find that we are just trained on ImageNet. And this is really useful because with this linear trend, we can basically subtract out how well a model does just based on its ImageNet accuracy. So the idea is the following: if you give me a new ImageNet model and I know it's trained on ImageNet, then I can just see, okay, if your in-distribution accuracy is 71%, then the expected out-of-distribution accuracy would be something like 58%. And this allows us to separate in-distribution accuracy from robustness. So the goal here overall is that if a model is truly more robust with distribution shift, it should behave like the screen star here. So it should be above the red baseline given by the standard ImageNet trained models. And we call this vertical shift above the red baseline effective robustness. And this is a reasonable goal because humans have high effective robustness on this distribution shift. We actually did this experiment specifically for the ImageNet V2 distribution shift. We trained and then evaluated 5 expert humans labelers on ImageNet and ImageNet V2. And they actually are exactly on this Y plus X line. So if the goal is to have a model that is as reliable as humans on this distribution shift, we want that the models have high effective robustness and also fall close to the Y plus X line. Okay, so this is going to be the overall measurement setup for this talk. And then the big question is, do any of the current robustness interventions that people have developed in the community that Aditi mentioned in the previous talk, do any of them achieve effective robustness on these distribution shifts in our testbed? Any questions about the setup? No? Okay, good. Then let's dive into the results. So the first part here is going to be natural distribution shifts, and we'll start out with the benign natural distribution shift. Okay, and as a starting point, to make this very concrete, what we're looking at, we'll get started with the ImageNet V2 distribution shift. Maybe some of you have seen this before. This is a paper I did back during my postdoc at Berkeley. And here we asked the questions, how reliable do current ImageNet classifiers generalize to new data from the same source? We wanted to recreate the original ImageNet creation process as closely as possible. So we got data from the same source, followed the same data cleaning process. When you do this with the original data set, you get 83%. And then, as I said, we followed the same data set creation process again. And the interesting thing was that we didn't get 83% out. Instead, what we got was 72%. And this is an 11 percentage point drop that corresponds to about 5 years of progress on ImageNet. So quite a lot in the context of a data set that is really aiming to be as close to ImageNet as possible. Okay, this is just for background, what ImageNet V2 is. Let's look at the results in our scatter plot evaluation. And these are now all the 200 models in our testbed evaluated on ImageNet V2. So the red line is still fit to only the blue points. And now we have 2 more colors here. We have brown points, which are the robustness interventions, or models with robustness interventions, and we have the green points, which are models trained with more data. And now if you think like, oh, it's kind of hard to see the brown points and the green points, this is indeed the case because they all fall really close to the blue points. So as we said, the goal here is to have effective robustness, to be above the red line. And it turns out that all of the robustness interventions basically don't do anything on the distribution shift. They fall on the same baseline that is given by standard ImageNet training. The only models that stand out by a little bit are some of the green points here. So these are models trained on more data. Some of them a lot more data. So on the top right, we have a model trained on a Google internal training set, JFT 300 million. So as the name suggests, this model was pre-trained on 300 million images. And then it's a little bit above the baseline. The next cluster of points here above the line was trained by Facebook on 1 billion images from Instagram. They get 1 to 2 percentage points above the red line. And then we have one more model trained on full ImageNet, not just the 2012 competition data set, but all of ImageNet. So about 20 million images, and it's also a little bit above the red line. Okay, good. So this is a little bit sobering. The robustness interventions don't do much, but maybe there's something weird about ImageNet V2. So let's look at more data sets. So the next natural benign distribution shift that researchers proposed is ObjectNet. This is from a team of researchers at MIT, and they set out specifically to make a harder test set in the sense that they wanted to challenge how good the ImageNet models are on the on the object categories within ImageNet. And what they did was tell crowd workers, can you take a picture, for instance, of chair in the bathroom upside down? So they wanted to break many of the natural correlations that are in ImageNet. For instance, that chairs are upright and the chairs more crowded in the bathroom. So this is a very interesting data set. And we thought, okay, great. We'll plug this into our test bed and see what we get. And this is again the corresponding scatter plot. So all 200 models in the test bed evaluated on ObjectNet on the y-axis now. And sort of the first impression here is that this still looks pretty similar to the plot we've seen before. So the red line, so there's a clean linear trend, the red line, it's fit only to the blue points. And there's still a couple of green points that are a little bit above the red line. Not much, a couple percentage points, but again, training on more data does give you a little bit of effective robustness here. Okay, let's look at two more examples, ImageNet Sketch and ImageNet R. I've paired those up because they're quite related. Here the idea is researchers collected, instead of real images for ImageNet, sketches. So they went to Google image search, Googled the 1,000 with the term sketch, and then stored the resulting images they found. So this is the ImageNet Sketch data set. And then ImageNet R is a supercharged version of ImageNet. So the R stands for rendition. The idea is that now ImageNet R contains many different kinds of renditions, not only sketches, but also paintings or like sculptures, anything but the real object is there here. And then again, we can take these test sets, feed them into our test beds, so we can evaluate the 200 models on them. And now there's more diversity. So the blue points still follow a nice linear trend, the red line. The green points here, the models trained on more data, still stand out as the best models, have the highest robustness to this distribution shift. Some of the brown points now also offer some robustness. So these are models with various types of data augmentation, and they give you a little bit of effective robustness. And then I have separately broken out the adversarial training models here. These are the yellow points. Because for some reason that I don't know, but this happens for ImageNet Sketch and ImageNet R, somehow adversarial training does give you a lot of robustness on this ImageNet Sketch distribution shift. It's a little bit tricky because you do sacrifice in distribution accuracy, but yeah, I think it would be very interesting to understand why the adversarial trained models are so good here. Specifically, it's 3 models from one paper. So some of the ImageNet adversarial trained models have less effective robustness. These 3 are all from the same paper, this paper on adversarial training on ImageNet with a denoising layer, and somehow that ends up being very robust. But overall, if you look at sort of like, okay, what does best overall, it's still clearly the models trained on more data. And the same is also then true on ImageNet R. So on the top right here, you have the cluster of models trained on a lot of data. They give you a lot of effective robustness. And then some of the models trained with adversarial training also give you some effective robustness. Good. So this was the cluster of test sets in the ImageNet context that people collected to see how robust models are to natural distribution shift. Let's have a look at the next cluster. So this is still real images, but now collected with an adversarial process. What do I mean by this? Specifically, I'm referring to a data set called ImageNet A. So this was collected via adversarial filtering. What does this mean? So the idea is the researchers started with a data source of images that were all correctly labeled, and then they filtered them through one specific model. So you take all of your correctly labeled images, send them through a ResNet 50. If the ResNet 50 correctly classifies the image, then you discard the image from the test set. So the only images you keep in your test set are those on which a ResNet 50 makes an error. Okay, so by definition, a ResNet 50 is going to get accuracy 0 on this test set. The interesting question is, what are other models going to do? And again, we ran all of our 200 models on this test set, and this led to a really interesting graph because so you have a sort of like knee-like shape now. It's not a single linear trend, but it's sort of piecewise linear. So the vertical dotted line here, this is the accuracy of a ResNet 50. And what we see is that everything before ResNet 50, so models that get the same ImageNet accuracy as a ResNet 50 or lower, they also have really low accuracy on ImageNet A. But then the models that came after ResNet 50, they very quickly make progress on this data set. It doesn't matter if it's just trained on ImageNet or if it's trained on more data, all of them follow a pretty steep linear trend here. So the idea is that for every percentage point of progress on ImageNet after ResNet 50, you get about 8 to 10 percentage points of progress on ImageNet A. So this data set looks hard initially in the sense that there's a large accuracy drop. At ResNet 50, it goes to 0, but then for the later models, they quickly close that accuracy drop. Good. So this was the first part, natural distribution shifts. So these were real images. Now for the next few minutes, let's look at synthetic distribution shifts. So distribution shifts where people intentionally perturb the images on a computer. And there we look at two kinds of, or like researchers proposed many different image corruptions. We collected the image corruptions from two different papers in our testbed. One of them is ImageNet C. So this is something people have probably heard before. This is now a widely used ImageNet test set, and it contains corruptions like Gaussian noise, other pixel-wise noise corruptions, various weather patterns like snow or fog or rain, and then various blurs like zoom blur or motion blur. And another paper that came out around the same time has a different set of sort of single processing motivated image corruptions. And then again, you can take all of these image corruptions. So like in what we did in this case, we averaged over all of them, and then you get the following plot. So interestingly, it's the same thing as before. The blue points, the models just trained on ImageNet, follow a nice linear trend. So this is the red line here. And then this time, training on more data actually doesn't give you any benefits anymore. So the green points here, the models trained on more data, that did quite well on the natural distribution shifts before. They now fall on the same linear trend as the models that are just trained on ImageNet alone. Instead, the models that stand out here are some of these brown points, and the ones that achieve the highest robustness are all special kinds of data augmentation. So like the more sophisticated data augmentation you do here, the more robustness you get to these corruptions. So as a baseline, one type of corruption that we just ran here was, what if you take Gaussian noise plus contrast plus motion blur plus JPEG noise, take those four corruptions as a data augmentation you do while training, and then you sort of roughly get the same amount of robustness as the deep augment and auto augment augmentations. And then if you look in the lower accuracy regime, the models trained with adversarial training do give you again some amount of effective robustness, but the problem is you also give up a lot of accuracy to begin with. So if you actually want to do well on these distribution shifts, then probably going with data augmentation is the way to go. Okay, good. And now let's go to the last part of our four quadrants. And this is synthetic distribution shifts that are explicitly adversarial. And this is good old adversarial examples, right? So it's clearly something we do to the images in a computer. We apply a small synthetic perturbation. And now this perturbation we apply depends explicitly on the model that we are going to evaluate. So like the simplest thing you can do is just take a gradient of your loss function to change the logits. This is FGSM, the fast gradient sine method. And then you can, people have seen this before, Aditi mentioned it, then you can easily flip the label of a current classifier. And then again, if you look at what happens in our testbed, this is what you would expect. Now, the models that do outstandingly well are the models trained specifically adversarially, either with adversarial training, robust optimization, or with randomized smoothing. This is just what we had in our testbed. And then some of the models trained on more data either do actually a little bit worse than the baseline or roughly the same as the standard ImageNet trained models. Some of the models here with data augmentation also are trained with a little bit of adversarial training. This is why they are noticeably above the red line. Cool. This was a lot now. So let's summarize this quickly. But we can look at this again in this 2x2 picture. One dimension adversarial versus benign, the other one natural versus synthetic. What does best? So all of the robustness interventions that people have come up with currently only offer limited gains on a natural distribution shift. So for ImageNet V2, ObjectNet, ImageNet R, and so on, the best thing you can do at the moment is just train on a lot more data. Collect a bigger pre-training data set and then fine-tune on ImageNet. Data augmentation helps on some of the natural distribution shifts. It does best overall on the synthetic and benign distribution shifts, like the image corruptions and so on. And then for the adversarial and synthetic quadrant, like adversarial examples and so on, this is where the robust optimization ideas do best. Cool. Any questions about this so far?
Is there any fundamental difference adversarial and distribution shifts in that? What kind of performs very differently? A more in a house distribution shift. Things only have sort of optimization house have sort of
yeah, that's a really good question. Let me just briefly repeat it to make sure the people on Zoom also get it. So the question is there a fundamental difference between the adversarial perturbations and natural distribution shifts? Because it seems like how they behave in terms of these evaluations looks quite different. And yes, I think they do behave very differently. As we said, the generation process is very different, right? Like in one of them, you actually really need to know the model and you specifically optimize your corruption for that model. And you also often, at least in the current adversarial robustness literature, have quite specific perturbation sets, like L2 perturbations and infinity perturbations. So I think the takeaway here is that perturbations that occur naturally in real data, like ImageNet V2, ObjectNet, and so on, they just seem to have a quite different structure. I don't know what the structure is. I would love to be able to tell you. This is more sort of like, let's just measure everything that's out there to see what's going on with real data. And then I think what you're raising is a very good question as a next step. What's like, why are they so different? Can we bring them together? Or are there some fundamental reasons that they just behave differently? Yes. Thanks. Hello.
I was wondering, so all of these plots, it's really just like easily see everything. But you're looking at just the accuracy, the top one accuracy. I'm curious if you did this with top 5, and particularly the other thing I'm wondering is that you did, instead of accuracy, it's like negative likelihood. Because I'm wondering, I'm imagining some of these models that they're still wrong in their prediction, but they're not so-called strong and wrong, right? They're less confident about the predictions, and so I think
that's a really good question. So again, just to repeat it for the remote audience, here in all of these plots, we always have top 1 accuracy on the axis. And a really natural question is what happens if you put, say, top 5 accuracy on the axis, or if you put log likelihood, as you mentioned, on the axis, to get a sense of like, are the models confidently wrong, or are they sort of like, do they have a good notion of uncertainty? And for top 5 accuracy, I haven't looked at this as exhaustively as top 1, but when we looked at top 5 accuracy, it was basically the same. So I don't think top 1 versus top 5 makes a difference here. Now, when it comes to negative log likelihood and calibration and so on, I don't know. It's a great question. We have all of this data. You're welcome to look at it. I think this would be a really good thing to figure out. I vaguely remember us looking at this in a couple of instances, and it seemed like the models were all roughly equally wrong in their confidences as well, but I really don't remember the details. So I think this is really worth investigating in more detail.
Yeah, I guess the more serious question is a follow-up to this color models.
So the answer is You really need to ask Rohan, who is really amazing researcher. Like the first author on the paper now, he's a PhD student at Stanford. I mean, he really was a tremendously effective person on this project. And as you said, it took a lot of time to aggregate all of these models and distribution shifts. We sort of built first a little bit of infrastructure to make it easy, like data, set up a actual database and so on. But all of these evaluations are out there, the test bed is out there, and Rohan put a lot of effort into making it really easy to plug in more things. So if you want to plug in more models and run them on these 200 distribution shifts, go for it. And we are happy to help you. So if you want to check this out, you go to robustness.imagenetv2.org.
Great.
Cool.
When you use data, natural data to model, what percentage of the data
great question. Yeah, let's. I'm not going to go back to the slides now because it took me so long to click through. Okay, the question for the remote audience was how much more data did the models that were trained on more data need? So let's just quickly recap. The ImageNet training set is about 1 million images. The models that stood out noticeably had at least 10 times that amount of data, like the large full ImageNet trained models were 10 or 20 million images. And then the models that were doing well in a higher accuracy regime were trained on about 1,000 times more data, like 1 billion images. Yes. We'll go back to how important data is in a minute. This is a really great question, how much more data you really need. So there's going to be a surprise in 1 or 2 minutes. There's a question on Zoom. Let's go to Zoom. Thanks, Aditi. Would you expect the problem I want to recognize objects taken by different cameras to look more like synthetic or more like natural perturbations? More like natural perturbations. I mean, okay, this is interesting. If you have a really good model of your camera noise and you can use this as data augmentation, and I would say go for it. I think then probably data augmentation is a good way to go. If you don't know what the variations across your cameras is, then it's probably going to behave more like the natural distribution shifts. Cool. In the interest of time, thanks a lot for all of the great questions. Let's continue because I just promised a small surprise at the end. Cool. So all of this was, just to be clear, all of this was only in the context of ImageNet. There are obviously many other interesting data sets out there that people have proposed. We focused very specifically on ImageNet in this paper because there were just so many models and distribution shifts already available. But I think it's fair to say that the findings we have in this paper do seem to hold up more broadly across other evaluation settings. So there's one very nice paper that's called In Search of Lost Domain Generalization. And I'm just quoting from the abstract, they also found that we conduct extensive experiments using DomainBet and find that when carefully implemented, empirical risk minimization shows state-of-the-art performance across all data sets. So this is similar to what we've seen also on the natural distribution shifts, which is the closest thing to their setting, that just standard empirical risk minimization is actually a very hard baseline to beat. And again, they also worked in image classification, and there's a question, what happens once you go beyond image classification? Other researchers have looked at similar phenomena in MRI reconstruction, for instance. We looked at it in the context of pose estimation. Other research, again, looked at it in the context of object detection. Overall, it seems like these trends hold more widely beyond image classification and actually also beyond computer vision. So in another paper during my postdoc, we looked at natural language processing, specifically question answering and the squad data sets, basically also constructed distribution shifts for these data sets, and then overall the trends are similar. In the interest of time, I'm not going to tell you about more of the details there. Instead, let's go back to the question we had and talk a little bit more about the role of data, because at some level, this seemed initially quite pessimistic to me. Like we have sort of a 12% accuracy, 10 to 12% accuracy drop on ImageNet v2, and then training on 1,000 times more training data gives you about a 1 to 2 percentage point increase. So if we say we want to fully close this gap and get to where humans are on the y=x line, this would mean you need sort of like 10 to the 10 to the 10 to the 15 more data. I mean, this is a silly amount of more data. So initially I thought, okay, maybe we really need new ideas there. But since then, there have been some really interesting developments that we're going to talk about now briefly in the second part of the talk. And what happened was that OpenAI released their CLIP model. And this is a really, really interesting paper for a variety of reasons. One of them is that they did exceedingly well on all of these distribution shifts that we just talked about. Let me make sure I get the question here. Oops, Aditi. Okay, thanks, Aditi. Okay, they did exceedingly well on all of these distribution shifts. So now you're an expert, you know all of them: ImageNet v2, ImageNet R, ObjectNet, ImageNet Sketch, ImageNet Adversarial. This is straight from their blog post, so they evaluated on all of them, and they also did their evaluation on this effective robustness framework. So they compare the accuracy of CLIP VITL, their largest model, to an ImageNet trained ResNet 101. So that on ImageNet, the two models have the same accuracy. So basically look in the scatter plot, we are looking at a certain X value, and then you can look at all of the out of distribution accuracies. And the CLIP model just did exceedingly well, like 6% is half of the drop on ImageNet v2, and then on the other distribution shifts like plus 50%, plus 40%, plus 35, plus 74. Like if you follow these competitive image classification benchmarks, you rarely see double-digit improvements. And then at plus 50%, I mean, come on, you can only do this like once. If you do it a second time, the data set is solved. So I found this really, really cool. And in their paper, they also illustrated this with scatter plots, again, following our evaluation framework: x-axis ImageNet, y-axis, they just averaged over 7 natural distribution shifts. The blue line here is the baseline ImageNet training. And then what they got with their CLIP model is the orange line. So the orange line here is basically a zero-shot evaluation with their CLIP model. And you can see that this is vastly more robust than any of the models that came before. And this raised many interesting questions here. One of them is just what makes CLIP so robust? And then the other, can you improve fine-tuning? Because there's a catch in all of this. The orange line that is really, really robust is when you, this happens when you evaluate CLIP without fine-tuning, so in the zero-shot manner. And if you actually fine-tune the CLIP models, then you make the model better on distribution data. So you move on the x-axis, but you actually make the model worse on the y-axis. So you're sacrificing robustness to improve your in-distribution accuracy. And then the natural question is this necessary, or can you get the best of both worlds? So improve in-distribution accuracy from fine-tuning while maintaining out-of-distribution robustness. Cool. And this is something my group has worked on over the past year. By the way, Aditi, just for context, how long do I have? Let's not go into a coffee break, ideally. I just forgot when we said the coffee break starts. It's okay, let's go a little bit longer. Okay, so first question is, where does CLIP's robustness come from? And the key question at a high level for us was, does this come out of the pre-training data set, or is it the language supervision? Because at a high level, the big innovation with CLIP was that they were able to train a large model on paired image text data. So one hypothesis was that just training on multimodal training on image and text data already gives you more robustness. The other hypothesis was, no, it's just about the fact that they have a more diverse image data set as pre-training data, and this is where the robustness comes from. And then what we did as an experiment was the following. We went back to ImageNet and we augmented ImageNet with original text from Flickr, right? A good chunk of ImageNet was collected from Flickr. So we connected the ImageNet images to the corresponding Flickr pages. And then we could get the caption data from Flickr for those images, and then do image text training just on ImageNet with the original Flickr captions. And then what you get in these scatter plots are these green points here. So the blue line again is the baseline just train on ImageNet, standard supervised learning. And now if you do image text pre-training on ImageNet, you get exactly the same robustness behavior as just training supervised on ImageNet. So you get less robustness than what you do if you do CLIP pre-training on their data set. We also have more experiments. Overall, the conclusion of this is pretty clearly that it's all in the image part of the pre-training data. The language supervision is important because it allows you to train on a more diverse pre-training data set, but language supervision in itself does not give you robustness. And then the second part was about fine-tuning. Can you fine-tune CLIP without losing robustness? And the answer is yes, and it's actually very, very simple. So just a schematic plot here again, x-axis in distribution accuracy, y-axis out of distribution accuracy. When you fine-tune CLIP, you move to the right, which is good, but you also move down, which is bad. And can you basically just move right and stay at the same y-axis value? And the answer is yes, and it's actually very, very simple. You just take the two networks, the fine-tuned one and the zero-shot one, and you linearly interpolate between the two. That was surprising to me because the whole point of neural networks is that they are non-linear. So why would you want to interpolate linearly in the weight space of two neural networks? But Mitchell and Gabriel, the leading authors, they are very creative experimentalists. They were like, oh, let's give this a try. And then it worked surprisingly well. So basically this pink curve here is what you get as trade-off between in-distribution and out-of-distribution accuracy as you vary the mixing coefficient between the zero-shot model and the fine-tuned model. If you want to learn more about this, you can actually go to our oral on Wednesday. So Gabriel is going to give an entire talk on this. So I'm going to keep it short now, also in the interest of time here. And I'm just going to tell you, yes, this basically allows you to improve out-of-distribution accuracy compared to what we had from OpenAI with the CLIP models. And then we improved this fine-tuning via weight space interpolation technique more. And this also led to the state-of-the-art model on ImageNet as of a couple of weeks ago. Cool. So now we had 40 minutes. So let's conclude. If you take a step back over the past, say, 5 years, there's been a ton of really interesting work in the robustness community. We have figured out all sorts of interesting ways to probe how well neural networks generalize out of distribution. And now, a natural question is like, how are these different robustness notions connected? And I think what we are beginning to see is that making a network more robust to one kind of robustness often doesn't transfer to other kinds of robustness. So many of the robustness notions that people have proposed are currently orthogonal. There are some consistent trends. For instance, we have seen that many of the natural distribution shifts benefit from larger and more diverse pre-training data sets. So CLIP, for instance, didn't just make progress on one out-of-distribution test set, but it made progress on all 7 of the natural distribution test sets that we have. I think overall what we need there is a more fine-grained understanding of the different robustness notions. But if you tell me, okay, in my application, I have this robustness problem, then I can tell you, okay, you should do these interventions or pre-train on the data, and you will get the best robust model that we currently have. And as I mentioned, so one really interesting direction I think at the moment is how can we improve the pre-training data? So in all of the natural distribution shifts that we looked at, we saw large improvements from pre-training on more diverse image data. And I think this is something we currently, as a community, have relatively little guidance for, right? All of the research we typically do happens in the context of one or a couple of benchmark data sets. So someone gives you a training set, and then we iterate on the model side to improve the accuracy. So what we ask less often is, okay, if you give me a model, what is the best pre-training data set if I want to do well on a range of out-of-distribution test sets? I think there are many interesting research questions to be asked there. And I think with CLIP now, it's much easier to experiment on the varying pre-training data sets because we don't have to do as much data annotation anymore. We can just use the image and text data of the internet and then see if we can build a good pre-training data set from that. Cool, then I'll put 2 more links here. One is the one I already mentioned. If you want to play around with these scatter plots and the robustness test that we assembled, you can go to robustness.imagenet-v2.org. And if you want to play around with CLIP and sort of like train your own CLIP models, we also, together with the people at Liang who build a data set, we also build a open source CLIP reproduction specifically for training. So you can already start training small to medium-sized CLIP models on, say, 4 or 8 GPUs, and we are currently in the process of scaling it up. So if you have hundreds of GPUs, so you can also train on hundreds of GPUs. Cool. That's all I have for now. So I'm happy to take questions, and thanks for listening.
It seems that the large-scale data costs the most for the last distribution. What is the future opportunity in the research for the last? I can just scale the data and solve it.
It's a great question. So the question is, what's the future research here for robustness? We can just scale the data and solve it. And I think at a high level, yes, I think data is very promising. I don't think it's as simple as we can just train on all the data, because already for these large, we have more data that we can train on. I think this is the main challenge. Like when the Liang team built their Liang 5 billion pre-training data set recently for image text pre-training, they collected more than 30 billion image and text pairs, and they somehow had to select a subset of 5 billion for the data set, because even the very large research labs at the moment don't train on more than a billion images, or maybe a couple billion images. I think the largest thing I've seen was the basic model trained on 6.6 billion images. So the point is, we have more data to pre-train on than we can actually pre-train on with current computational constraints. So I think finding the right, really good pre-training data set is a really interesting question.
So I think like some of the initiatives you were showed is at least I think like the gamification of benchmarks, like people were overfitting to the validation set, and like the current robustness benchmarks is sort of still built in the same way of like you can theoretically like game some of these robustness benchmarks. So I guess I'm wondering, do you think that this like traditional benchmark setting is still like the best method to evaluate robustness?
That's a good question. And just to clarify a little bit, what were the, so like, at least my interpretation of ImageNet v2 actually is that people didn't overfit to ImageNet at all in the traditional sense of overfitting to the test set. So like when we built this, the worry was that better ImageNet models would not do better on ImageNet v2, that it would be sort of this plateauing trend. But what we found was that every percentage point of progress on ImageNet did translate to an equal amount of progress on ImageNet v2. And so it's indeed the case that the drop is a problem. There is a noticeable drop, and the models need to be more robust. But I think in terms of gamification of these benchmarks, I've become a big fan of these benchmarks, because it seems like if we make numbers better, they do get better also on adjacent distributions. And the CLIP model is, I think, a great example of that. But this like climbing of benchmarks still leads to good progress. So I'm at the moment not too worried. I mean, maybe at some point we need more challenging out of distribution test sets once the current suite of test sets is exhausted. I think overall it's going in a good direction.
Go back to the from the big dog, like where they show that improvement, so you talked about distributing from language so there's another important change that so one of them is less than 1 and the other is very large. There's another big change here. So like, because these two models, they might be going to different classes and so on. So I think this is also very important change. So this improvement might also become from because they're going from CNNs to transformers. So
yeah, that's a great question. So the question was, is the robustness maybe coming from vision transformers versus ResNets? And the answer is no, we know it's not coming from that in a very precise way. And actually the CLIP paper already pointed it out. If you look at these trends here in their own scatter plots, like let's say just look at the orange line, there are about 8 or so points here, maybe 9. And these are both vision transformers and ResNets. So they get the same large robustness gains regardless of architecture. And this is also what we had found before. If you look at the blue baseline, if you like, the architecture doesn't matter. All sorts of different architectures, including vision transformers, have the same robustness trends. Well, good question. Thanks.
Follow up on that, I have a question about I probably missed this, but so what was the gain
yeah, I think their pre-training data is really good. So, yeah. So we don't know exactly what's in the pre-training data set. They didn't release it. When we talked to them, they were like helpful and gave us some idea of what's in there, but they can't say exactly what sources, for instance, and they can't release the data. I know that they spend quite a bit of time building this pre-training data set, so it's a good one. And from some early results of the Lion data set, we also know that the Lion data set for the larger models seems to be a bit worse than the CLIP pre-training data set. Lion is close, but CLIP is a bit better. So I think a lot of the secret sauce here is really pre-training data set.
I also want to, I don't know, so a lot, it's talked a lot about using robustness, right? One of the things that we've been planning also is to use this what you see is that when you try this in preparations, it doesn't really reflect on the shifts that you would actually see in real world, right? Because you have a manifold of the distribution, and you were one shift in that manifold, and just shifting across this product motivation. So we have gone to that, like, how they're being influenced in that direction. And how does that influence?
So let me just make sure I understood the question correctly. So you're asking, or you're saying you also ran experiments where you found that adding Gaussian noise, for instance, didn't help with robustness or natural distribution shift, and the conjecture is that this Gaussian noise is not really related in a productive way to the natural image manifold.
Yes.
Yeah, I think that's a reasonable interpretation. I agree with that. I think the big question is like, can we learn more about the natural image manifold to sort of like augment in a way that it follows that structure? And yeah, I don't know the answers to that. I would love to know the answers. If you have answers, let me know.
Okay, thank you. Thanks for the great talk. I have one maybe leading question and then follow up. Would you mind going to the slide with the flip results on the different ImageNet variants?
Yep.
Yeah, so for this, I'm wondering, why would we expect a drop in the first place in the setting between ImageNet and ImageNet V2, given that flip isn't actually trained on ImageNet V1, so it's not in distribution, outer distribution, they're kind of both equal, right?
Yeah, that's a great question. Let me repeat the question. So why, okay, for ImageNet trained models, ImageNet V2, there's a drop. Maybe that makes sense because the models are specifically trained to do well on ImageNet. Now, if you don't train a model to do well on ImageNet specifically, and you evaluate on both, why is one still lower? And I think the answer for that is that ImageNet V2 in a subtle way seems to be harder by a little bit. I mean, I can tell you some conjectures. We haven't thoroughly verified any of them, but for instance, it could be that on average, maybe in the ImageNet V2 test set, the size of objects could be a bit smaller. And maybe if the size of objects is smaller on average, then the models will do a little bit worse. So this would be great to figure out. Yeah, happy to tell you more about the details there. But I do think ImageNet V2 is sort of like, not for humans, right? It's the interesting thing. Humans get the same, but for models trained on web data, it seems like ImageNet V2 is a bit harder.
So then I'm wondering, given that all of these are of similar levels of in-distribution for flip, given that it's trained on some mystery subsection of the whole internet, is this really out of distribution robustness?
Oh, great, yeah.
And then also, do you think we need out of distribution robustness if we can train at this scale, or what's the role of that? I know you put the insert loss domain generalization slide, which is kind of tangential, just but I'm wondering what your thoughts on whether out of distribution robustness is still relevant given this scale.
Yeah, good question. So the question is like, what even counts as in distribution, out of distribution data if you're pre-training on extra data anyway? And I agree, this gets pretty muddy. So I actually typically don't think of it really like in distribution being the training set and out of distribution being different from the training set. I think of it as more like, okay, we have a reference distribution ImageNet, and we have these variants of ImageNet, and it's a natural goal that a model should do equally well on all of them because humans can do that. So I just want to make sure that basically on the shift from ImageNet to these others, we see small accuracy drops. And then it's basically, we're still evaluating on the same test set. So I still call this out of distribution robustness. And it's also clearly a distribution shift. And I think it's still a very important goal because, I mean, sure, we can pre-train a lot more data, but it doesn't automatically mean that we do better. We need to make sure that we actually have good coverage with our pre-training data and measure where we do well and where we don't do well.
So you think it's more about measuring that it kind of does about the same on data sets you would hope it to be about the same one rather than actual stuff that differs from the training distribution?
I mean, both are important. And we don't have good ways of quantifying how different it is from the training distribution. Right. So that makes it complicated. I mean, in the end, I think everyone will agree that the goal is we just want to have high numbers on all of these data sets, right? And then sort of like how you exactly slice this apart for understanding what makes the models more robust. I think that becomes a bit more sort of like how you approach this research question. in the past, I found it very useful to look at the drop relative to ImageNet in order to understand what techniques really help you with robustness. And just to illustrate this a bit more, one thing that's nice is that if you look at it in terms of this effective robustness and gain above a baseline, this is a scale invariant property largely. So when we found this improved fine-tuning technique, we made all of the experiments on small models. We saw that it was above the line on small models. The accuracies were bad, but it was above the line. And they gave us enough confidence that this is a real improvement. And then we just handed it over to the collaborators at OpenAI. They ran it on their largest model, and it worked on the first try. So this is why I think that looking at things relative to a baseline, at least from a sort of like scientific discovery process, is pretty useful.
Cool. Thanks so much.
Cool, thanks.
Hi, thanks for the talk. I just had a question regarding your last. So, all the results so far are sort of like blind or zero sum evaluation of the
Yes.
Has there been any work in terms of if we incorporate some amount of data from the upper bound domain, if we train on all the data, but we incorporate some amount of data, has there been any work on what
Yeah, that's a really great question. So a very natural, so the question is about transfer learning, basically, and a very natural sort of like conclusion here is like, oh, there are large drops out of distribution. Can we solve this at least partially if we start using some labeled examples from the target distribution? And I think, yeah, that would be really interesting to understand for all of these OOD shifts, how much you can gain from fine-tuning on them. I don't think anyone has done that, but the data is out there. I think people have looked at that in the context of another distribution shift challenge dataset. So in Wiles, I think there's an update of the Wiles dataset where they also added some unlabeled data from the target distributions. And I think at a high level, for the datasets in Wiles that I know better, pseudo labeling the best. But for the datasets that I know better, also in the end, you just can do clip, fine tune on the respective distribution data, gives you the best performance overall. Oh, the two datasets I was referring to are FMOW and wildcam and Wiles.
Thanks for the talk. So it seems to me that most of the robustness research is performed on independent for other classification tasks. I'm wondering how much the insights that are gained here could be transferred to localization, segmentation, deep point estimation, that sort of tasks. Like, are properties different there? Or?
Yeah, that's a really good question. So basically, what about other computer vision tasks? And also, just as an apology, my background is more like in sort of like Europe's ICML machine learning, and this is why I start always with classification. I think it's a really interesting question to what extent other tasks show similar phenomena. And I would love to see more work on this. I can tell you a little bit of this. I only briefly mentioned it. These are some evaluations I know where people have made similar scatter plots with an out of distribution test set for MRI reconstruction, 6D post estimation, object detection. And it looks like at least these linear trends as a baseline do occur in all of these settings. I think overall, I don't also know what people have proposed as robustness interventions for object detection and so on. I just don't know the literature as well. I guess we know it better. So I would be very curious to see if similar trends hold up there as well. Cool, thanks. Cool. Any more questions? Let me quickly check the chat. I have one direct message on Zoom, so maybe I'm not going to read that one out. I'm not sure if it's meant for everyone. I think now's the coffee break, so let's do a break. And then Aditi, can you remind me when we are back?
Hi everyone, and welcome back. So the second or like the third part of the tutorial, I guess now we'll have Liang joining us virtually, Liang and Weijian. They're going to talk to us about how do we evaluate models under distribution shift when we don't have labels. And with that, I'll let them take it away.
All right, thanks. Hi, everyone. I'm Liang. I'm from Australia. Good evening. So normally I would share this talk with my student Weijian, but looks Weijian doesn't feel very well today. So I'm going to give this talk by myself. All right, so we're going to talk about model evaluation under out of distribution data, especially without labels. So In today's talk, I'm going to talk about, first we'll recap classical model evaluation as done in Ludwig's overview slides. And then we review some distribution shift and out of distribution test sets. And then we talk about dataset similarity and dataset representations. And finally, we're going to talk about evaluating models on unlabeled out of distribution data. All right. So as said, evaluation in machine learning is a pillar. It is very important and very fundamental. So usually we assume that the training set and test sets are independent from each other. Oh, sorry, what's that? Okay, so we are also assume that the training and test sets are identically distributed. So during training, we use sort of learning method to obtain a machine learning model. And in testing, when we want to evaluate how well it performs on previously unseen data, we evaluate our model on this previously unseen test set, and we obtain its performance. So it's very standard from our textbook. So we call this type of evaluation supervised evaluation, where we have labels, test labels. So for example, we have a few test images, and on the left and on the right are their labels. So when our classifier makes predictions, we compare the predictions with the ground truth labels and see whether they are the same. So in this example, our classifier gives us accuracy of 33%. Okay, so so this type of evaluation is what we normally see in our textbook and in most of our public data sets. For example, in ImageNet, MS Coco is public data sets where when we perform in distribution evaluation, we use the test set together with the ground truth labels. Okay, so with these public in distribution benchmarks, this sort of evaluation that we see in the textbook is feasible because the test set is fully labeled and the training and test sets are usually from the same distribution. However, the problem arises when we consider out of distribution data, especially without ground truth. So also introduced in the overview slides. So now we use again the autonomous cars as example. So we train the self-driving system in one city and we try to deploy this system in another city, which is very different from this source domain. So we could encounter lots of different test distributions. They are all out of distribution from our source domain. So lots of different weathers, city conditions, sorts of things. So in these scenarios, our textbook way of evaluating models might have problems. So the problem is that our test environment or our test sets do not give us the labels, the test labels. So that means our test images are unlabeled. So we sort of encounter this problem very often in computer vision applications. So for example, we deploy a face recognition model in lots of new places. We deploy a detection system to lots of new cities. So we encounter this out of distribution test data, unlabeled test data very often. So in these scenarios, we can't quantitatively measure the model accuracy like we usually do. And if we want to measure the model accuracy, we usually have to annotate the test data. but the test environment keeps changing, so we need to annotate data again and again. So that's very expensive to do. So this is the problem that we are looking at. That is, can we evaluate our model's performance in unlabeled out-of-distribution test data? Okay. So what we want to do is evaluation beyond the textbook, out-of-distribution and unlabeled evaluation. So, so suppose our test set is unlabeled. So that means we are only provided with images, test images. So let's see some examples below where we have unlabeled test set 1, unlabeled test set 2, unlabeled test set 3, and unlabeled test set n. So we want to answer the question, how can we evaluate our models? How can we obtain our model accuracy in these unlabeled test sets? So this is the question that we want to ask. Okay, so now let's formally define this problem. So suppose we have a training set. This is our training set, which is fully labeled. It's standard training set. So we train a classifier on this training set. And then in the standard evaluation, model evaluation, we have a labeled test set, which is on the left, a labeled test set. So we can very easily compute the classifier accuracy on this labeled test set. So for example, our accuracy is 98%. So the problem that we are looking at is unlabeled test sets. So we evaluate our model on its unlabeled test sets. Can we obtain the model accuracy on this test set? Okay, so in summary, we are given a training data set and a classifier trained on this data set. So we are also given a test set without labels. So we want to estimate the classifier accuracy on this unlabeled test set. So, so if you are familiar with model calibration, you would somehow come up with an idea using sort of a calibrated model. Can we use a calibrated model to directly obtain our model performance on this unlabeled test set? For example, when we have unlabeled test set, we calculate the average confidence of our model. So for each image, we compute its prediction confidence, and for all the images, we compute the average confidence, say it's 30%, for example. So if it's a well-calibrated model, then we could somehow say our test accuracy equals 30%. If the model is well calibrated. So, so this is a sort of, at first thought, it's a feasible way. Just we calibrate the model and we use the model confidence to indicate the model accuracy on this unlabeled test set. However, the problem is that, the problem is that usually our networks are miscalibrated. So it somehow means that, so in many scenarios, it means that our calibration methods actually are less effective under distribution shift. So actually, this is a very active field of research, how to do model calibration in out-of-distribution data. So it's quite challenging. And so far, we don't have a very satisfying solution to this problem. So so the idea of using a calibrated model to estimate model performance in unlabeled test sets is still not very feasible. Okay, so so how about other solutions? Okay, so now let's talk about other solutions. So in my talk, I'm going to give you some overview of what the community has been doing on this problem. So, so a very intuitive solution I'm going to talk about is to predict the model's accuracy based on distribution shift. So let us look at the example. So we've got a training set and we've got a classifier trained on this training set. So suppose we have 3 test sets. The 3 test sets, none of these test sets have labels. So I want to ask a question. So on which test set the classifier performs the best? So the answer is quite obvious. Test set A would be the set where our classifier performs the best because it looks exactly the same with the training set. So our classifier will perform the best. So so the answer is, yeah, test set A. On test set A, our model will perform best. It has 90% accuracy because test set A is very similar to the training set. So then we can observe that test set B is sort of, different, slightly different from the training set. And the reality is it has sort of accuracy of 70%. Okay, so if we look further, we look at test set C. So test set C is very different from the training set. And somehow we can get its model accuracy on this test set C as 20%. So it is, consistent with our feeling and with what we have found in the literature that the more different your training set, test set is from your training set, then the lower accuracy your model will have. All right. So so this is suggested, or this observation is used by many papers in domain adaptation in field where when you have a big domain gap between the target and source domain, your model will probably have lower accuracy on the target domain.
Sorry to interrupt, Liang. There are some questions on the Zoom chat. So if you could just briefly read out the question and answer, that would be great.
Right. Yeah. So Nimisha, so your question is how to calculate the similarity? How is distribution shift quantified? This question is exactly what I'm going to talk about in my next slides. All right. So literature tells us qualitative relationship between domain gap and classifier accuracy. So I'm trying to talk about how can we quantify this relationship. Okay. So now we want to do some correlation study. So so in our correlation study, we want to study the relationship between dataset distribution shift and the model's accuracy. So to perform this correlation study, we first collect lots of test sets that are from lots of different distributions. This is the first thing. And the second thing is, so for each test set, we obtain its distance to the training set, and we obtain the model's classification accuracy on this test set. And the third thing is, after we do the first two steps, we have the third step. That is we plot the relationship between the test accuracy and the distribution shift. All right. So this is the three things that we want to do. So in answering the question raised just now, so for this correlation study, we use very simple feature distance, which characterizes the distribution difference between two data sets. So so this distance basically gives you a scalar, so that this number will indicate how different your two data sets are. Okay, so so we want to do this correlation study, and to do the first step, we must obtain lots of test sets. So how can we do that? We simply use image transformations. For example, we have original data set, which is shown here, a data set. Then we apply lots of image transformations where we can synthesize technically unlimited number of synthetic data sets. So by applying different transformations, synthetic set 1, synthetic set 2, synthetic 3, 4, 5, sorts of things. So another example, we start from an original set and we can synthesize a lot of different synthetic data sets from this original one by simply using image transformations. So this is how we obtain lots of test sets. And the second question, in order to study, to do this correlation study, how can we obtain our classifier accuracy on each of these test sets? So, so basically, our answer is also very simple. The synthetic data sets we just saw, they have the same labels with the original data set. So basically, if we go back, then we see the synthetic data set, for example, synthetic set 1. So every image is contains the same object as the original image. So you see, basically, you see the labels of the synthetic data sets are the same with the original data set. So we can have labels of all these synthetic data sets. So once our classifier is trained, we can easily calculate the classifier accuracy on every synthetic data set. Okay, so so we've done the 2 steps. Now we calculate this correlation study. So so let's look at the leftmost figure. So the x-axis is the feature distance, which characterizes how far your test set is from the training set. And the y-axis is the test set accuracy, is your model's accuracy on the test set. So in this figure, every point is not a model. Every point is a data set. So every point here is a test set, basically, or you can call it a synthetic set. So every data set here is represented by 2 numbers. Its feature distance to the training set and its classification accuracy, where we test our classifier on this test set and we obtain the classification accuracy. So basically, we can see a sort of a negative linear relationship between the classification accuracy and the feature distance, which is consistent with what we expected. When your test set is very far from your training set, where the feature distance is larger, then you can, there's a bigger domain gap, and your model will probably perform worse in these difficult test sets. Okay, so this is on the MNIST. We use the MNIST as the seed data, and we can synthesize, we can have this correlation study. So if we do it on CVPR 10 and COCO, so we observe similar trends. All of them are strong negative linear relationship between classification accuracy and the training test distance. Okay. So basically, these figures tell us that so our classifier tends to have a high accuracy on test sets which have smaller distribution shift from the training set, and this relationship is quite linear. Okay, so going back to our question, can we estimate or can we evaluate models' performance on unlabeled test data? So in practice, so for example, we are given a sort of unlabeled test set. We simply calculate its distance to the training set, and starting if we calculate distance here, for example, then starting from here, we can sort of estimate our classification accuracy on this unseen test set as 50%. Okay, I see a few questions in the chat. Okay, so from Arnold, any theoretical guarantee that synthetic data sets are sufficient enough to extrapolate into the out of distribution real data, and how many synthetic data sets we need? So this is a very good question. So actually, the first for your first question, any theoretical guarantee. So basically, this is one of the limitations of this sort of method. So usually you have to guarantee that you have to make sure that your synthetic sets are synthesized such that it spans as much space as possible, so that your new test set would sort of fall into this region. So suppose your test set is very unique. Your test set is sort of here, then this model will probably make a very poor prediction if your test set is very different from others. How many synthetic data sets we need to achieve this? So in this figure, I can't remember exactly how many synthetic data set we have, but it's sort of a few hundred, at least 1,000, I believe. So usually this number will give pretty good prediction result on some, for example, on some real world test sets. I'll show some result later. Another question is the feature distance measured in image domain or some feature domain? Yeah, we are using the feature domain. So we use the classifier to extract features for every data set, for every image in the data set. So the feature distance is computed based on the image features. From Kai, is this assumption valid on out of distribution data if the feature distance correlation is guaranteed? Is it still meaningful to study domain adaptation? Let me answer the first question. Is this assumption valid on out of distribution data? So yeah. So although these data sets were created from in-distribution data sets, so we will show later that they can be quite useful for out of distribution data. I'll show later show the results later. If the feature distance correlation is guaranteed, is it meaningful to study domain adaptation? So yeah, this is actually interesting question. So what we study here, so basically is to estimate test set difficulty. So we are not trying to improve the model's performance on the target domain. Instead, we are trying to estimate target domain difficulty. So this is quite different from what domain adaptation is doing. Okay, follow-up question. To put into context, let's say if your model was trained on daytime and unlabeled data was from nighttime, would you think synthetic data will cover this domain shift? So, so you would normally find some failure cases of this kind of formulation. For example, let's say following Aditi's talk, for example, if your test domain is adversarial, contains lots of adversarial samples. So this test domain will probably deviate a lot from what we synthesized, the adversarial test samples. So so in this case, this type of modeling would have limitations. It probably can't predict the adversarial test samples very well. So this is also a common problem for the literature in this area, where if your test set is super unpredictable, then it's quite unlikely to be its accuracy is quite unlikely to be estimated very well. All right. So go forward. Okay. So so previously we saw some linear regression, linear relationships. So a very natural thought is to use linear regression to model this relationship. So so basically we use this feature distance where its equations here. Basically it calculates when we have two distributions, it calculates their difference in their mean and in their difference in the covariance matrix. So, and this feature distance will give us a single scalar, which is one-dimensional scalar, to represent the difference between two data sets. And we use this feature distance as x-axis and use the estimated accuracy as the y-axis. And we simply use two parameters in this linear regression model. So it's very sort of straightforward. Okay, so so if we want to make it a sort of slightly more complex, we could use a sort of neural network regression where we use a slightly more complex representation. So this is our feature distance. And in addition to this scalar, we also concatenate the mean vector and some sort of covariance feature. So we have a higher dimensional representation of a test set. So we fit this higher dimensional representation of the test set into a neural network composed of a few layers of MLPs. So we can obtain the accuracy like this one. Okay, so this is a neural network regression method. Okay, so now let's look at some experiments. So for example, we have this. COCO training, this setup, COCO setup, where we use COCO training set to train our classifier, and we synthesize many test sets using the COCO validation set, and so we train this regression model, and we test this regression model on a few real-world test sets, like Pascal, ImageNet, and Caltech. So we choose the common classes with the COCO training set. So there are sort of 12 classes. Okay, so now let's look at the result. So basically, every bar means our accuracy estimation on a certain data set. For example, this is our estimation on the ImageNet dataset and ImageNet A dataset, ImageNet B dataset, and this is the ground truth accuracy. So if you suppose you have ground truth labels, then your model will have 88.8% on this ImageNet dataset. And if you are using this estimated accuracy, so it gives you sort of 5.6 error, absolute error. So basically, our model gives accuracy of around 83. So if you look at ImageNet A dataset, test set, the ground truth.
Yeah, sorry to interrupt,
Aditi.
Liang. We lost you for 2 minutes because Ludwig's laptop died.
Can you hear me now?
Okay, I think now we are back. And if you can just recap the last 2 minutes of what you spoke and go on, that would be great.
Right, that's fine. So the last 2 minutes, I was talking about this data set, test set settings. So we train on COCO training set and test on some real world data sets that have the same label space as the COCO training set, which effectively are 12 classes. So so basically, if we test our model, for example, on this Pascal A dataset, so the ground truth accuracy. So suppose we have the ground truth labels is 74%. So using our method, we can estimate. We could have very small estimation error, which is the y-axis absolute error. So 0.9% error. So we can make it very good estimate. So what is challenging is these Caltech datasets. So the ground truth accuracy is sort of 93, and our estimated one has 13% error from this ground truth accuracy. All right. So this is the result of linear regression. We only have 2 parameters. So if we look at this neural network regression, it is better than linear regression. So if we look at these figures, the green bar means the neural network regression, which are usually lower than the blue bar. So this is lower, and this is slightly higher. This is not good. This is lower, it's like higher, not good. So usually neural network regression looks better. It gives a smaller error. Okay, so this is the first method I'm talking about, and I'm going to talk about a few others. Looks like we've got a few questions.
Hey, Liang, I just have a quick question. When you're talking about the accuracy measure prediction rate, so the data sets, I'm not sure exactly how they were created. So I was just wondering, have you thought of cases where, like in the test set, you have labels that were not in the training, or is it just the same label set both in training and testing?
Thanks for the question. So basically, we assume the test sets have the same label space as the training set. So otherwise, if it becomes open set problem, so open set recognition problem. So we haven't looked at that problem yet.
Would you be talking about that eventually?
No, we are not going to talk about this open set problem. So I don't think there is a viable solution for open set model evaluation without labels. So okay. Yeah, so there isn't, as far as I know, there isn't research in that space yet. So so I think the current research is mainly focused on this closed set image classification.
Thank you.
All right. Okay, thanks. So for the second method, I'm going to talk about self-supervision.
More question.
Hello?
One more question, please. Just a follow-up for the previous one. You said that for OpenSet, there's no viable solution, and for this one, you assume that the set of labels is the same, right?
Right.
What about label shift? Like, what did you ever consider these cases when the distribution of labels is different? It's the set of labels is the same, but one of them becomes more common.
That's a great question. So in the current setting, we typically so let's look at this figure. So for the Pascal, ImageNet, and Caltech, so they we chose the same label space, and we assume that their label distributions are the same. That means for each class, they have sort of the same number, a similar number of images. So in the scenario that you described, so suppose we for example, for Pascal, it's somehow some of its classes have very few samples. For these scenarios, we haven't thought about, we haven't have a solution for that, but we are working on that. So we just talked about this problem recently. Yeah, we were discussing this idea, right? So this sort of structure differences, so label distribution differences. So these things are not taken into account yet.
Thank you.
But this is a really good question. So I can't answer you right now. So how to solve this problem?
Hey, Liang, just following up to my previous one is, have you tried this evaluation on Wild's dataset? Because that's like the new benchmark for distribution shifts, right?
Not yet. So the Wild's dataset, I think it was published in last year, right? ICML 21 last year, not yet. Because the paper I showed now was published in the same year, 21. So we didn't try that dataset. We can probably try that. But the thing is, what we really want to do is to try our this thing on real data sets. So synthetic data sets are fine, but we are probably looking at the real data sets, but we can have a try on the wild data sets.
Yes. I mean, Wild actually is like in the wild, so it's more real world, I would say more. I mean, yeah, Coco is also real world, but Yeah, thank you.
Yeah. So yeah, I'll take a look at that. So yeah, that's a good question. Thanks for that. Yeah, I was talking to my student a few days ago about this wild data set. Sort of, I forgot what it is about. All right, thanks. So okay, so the second solution is sort of self-supervision for this problem. So so I think Aditi mentioned rotation sorts of things. So for self-supervision. So yeah, so another solution for this so-called unsupervised classifier evaluation is to correlate your classification accuracy with self-supervision rotation, for example, rotation prediction accuracy. So what we do is, so now so in addition to our classifier here, in addition to our normal classification, semantic classification head, we also train a rotation prediction head. So so train a rotation prediction head, and we evaluate. So rotation prediction can be evaluated freely on any test set. So we want to explore whether this rotation prediction accuracy on the test set has a high correlation with this classification head. All right. So basically what we found, so let us show this figure again. So we have this rotation prediction head, and we have this classification head. So suppose we have test set 1, test set 2, and test set 3. So so what we found was that the rotation prediction accuracy from 1 to 3 drops is 95, 85, and 75. So correspondingly, the digit recognition accuracy also drops. It is from 90% to 80% to 70%. So basically, you can see sort of they go together. So again, we want to perform some correlation study. What we did was we collect many test sets of different distributions, and so for every test set, we obtain the semantic classification accuracy. So basically, it's the usual image classification accuracy using the labels on the test sets. And we also calculate the rotation prediction accuracy on every test set. So then we measure the relationship between classification accuracy and the rotation accuracy. Okay, so now let us show the result of this correlation study. So we also show 3 setups. On the left is CVPR10 setup, where on the x-axis is the rotation prediction accuracy, and on the y-axis is the classification accuracy. So again, you see a very nice positive linear relationship between the 2 accuracy numbers. So this sort of relationship applies to other domains as well. For example, is CVPR10, MNIST, and the COCO. So basically, it suggests that so our network, if it's good at predicting rotations, then it is very likely to be good at object recognition under the same environment. Okay. So once we discover this sort of relationship, then we can, estimate our object recognition accuracy from its rotation prediction accuracy. So similarly, it's very simple to design a linear regression model which only has 2 parameters, and using this rotation prediction accuracy as input and output this classification accuracy. All right, so these are some results in similar format as we've seen before. For example, this is our ImageNet test set. So normally its accuracy is sort of 87%. So its ground truth accuracy 87%. So using this method, we can calculate the absolute error, which is 2.27. It's pretty good. So what is more challenging is sort of like this Pascal A dataset, which normally it is 69%. So our estimate is sort of like has a 6% error from this ground truth accuracy. Okay, so this is so we also do this testing on this COCO setup with more test sets. So so basically we use this ImageNet V2 to test we test the model performance on this a few different versions of ImageNet V2. So so we've also, for example, this on this ImageNet V2 threshold 0.7, the ground truth accuracy is 92%, and the what we estimated is has very small error from this ground truth accuracy, which is 0.9% error. So the worst case is for ImageNet VID robust. So where the ground truth accuracy is 74, and what we estimated is 4% different from this ground truth accuracy. All right. So okay. So then another solution is we use sort of average confidence difference. So so the idea is very simple. It was published last year. So so if you have classifier, then you feed images from the space distribution and target distribution to this classifier, and you can very simply calculate the average confidence. So just the average of the image confidence of every image of this data set, and you have two average confidence numbers, one on the base distribution and one on the target distribution. And then it's also very simple to calculate their difference of confidence. So, so just calculate their difference. And this difference can represent the distribution or domain gap between the base distribution and target distribution. And this domain gap is sort of indicative of their accuracy, the accuracy difference. So basically, so this is a difference of confidence, which is through a regression method can be related to this accuracy gap, the model's accuracy on the base distribution and the target distribution. So so this method is also very interesting and effective. So for example, on this ImageNet dataset, so I sort of forgot whether it's ImageNet C or ImageNet other ImageNet dataset, probably ImageNet C, I can't remember exactly. So so this sort of method, these bars have relatively low mean absolute error. Okay. So there are also some other methods that can solve this unsupervised evaluation problem. For example, this paper is published this year, I think from UC Berkeley. So what they did was when they have auto distribution data, which is unlabeled, so they use pseudo labels for this auto distribution data and use these pseudo labels to train a model parameterized by this data. And they also use the training data to train this model parameterized by this data. And they simply calculate the difference, L2 distance between these two, the weights of these two models. And these weights can be very well correlated with the classification accuracy on out of distribution data. So shown in this graph. So basically on the x-axis is the L2 difference of these two models and of the weights of the two models. And this y-axis is the test error on the out of distribution data. So you can see for different types of data sets. So here, every point is a data set. So for all types of data sets, it seems like they follow a very nicely distributed like linear relationship. So basically, when you are testing your model, you can calculate this indicator, and this indicator can show you whether your model will be successful or fail on a certain test set. Okay, so there are also a few other methods that can solve this problem. So for example, adaptive threshold for predicting, so they use sort of adaptive threshold on this softmax output to predict this accuracy. And also some methods use use two models and using their agreement score to represent whether your samples are correctly classified. Okay. Okay, so I'm going to conclude my talk. So in this talk we discuss a very interesting problem, that is how to evaluate models without ground truth. And the community generally uses very simple methods now. So that is dataset level representations and regression. So these representations are usually very simple and very intuitive and interesting. So, and there are potential applications for this problem where we can apply it to generic computer vision problems like retrieval, detection, and segmentation, etc. As asked just now, there is also application scope limitations of these sorts of methods, where if we are using this sort of sample sets or sort of correlation-based, regression-based methods, usually we ask this regression to be done on these samples. These samples should cover the test sets that are of interest. Otherwise, there will be failure cases, for example, adversarial test sets. So another interesting insights that I want to point out is dataset representation. So it is a very much less studied problem compared with image representation that we study a lot. So the community now uses simple solutions, such as, for example, first and second order feature statistics and other very simple intuitive class dataset representations. So the question is, can we find better representations of datasets? So this is very challenging because a dataset is composed of lots of images. So it's much harder to encode a dataset than to encode a single image. Okay, so last thing is dataset similarity. So in this talk, we discussed this feature distance, we discussed the confidence difference and projection norm. So there are all methods to characterize the similarity between data sets. So can we, try other similarity measures, or can we even try to, sort of learn a similarity measure? I think that's also very interesting. Okay, so that's all for my talk. Thank you very much. I can see there are quite a few questions on the chat. One question from Than, any explanation why COCO has less correlation between rotation and classification? I'm not sure if Weijian has answered this question. Okay, so yeah, Weijian answered this question. So basically, looks like Cocoa has more diverse visual appearances than this MNIST and CVPR. So we haven't find out why this is the case, but probably because it's more diverse for the Cocoa data set. For Zhongwei, one more question. Based on your study, which one measures domain gap better? Difference of confidences or feature distance? So this is a very good question, actually. So the difference of confidence and feature distance. So I think, so let's go to that one. Difference of confidence. This is difference of confidence, and other methods, some methods use this feature distance. So we can't give you definite answer yet. The reason is that I think the community is yet to have a benchmark on this problem. So these papers are not directly comparable, but these methods are, the methods are, makes a lot of sense, but the results are not directly comparable. So I think it's important for the community to build sort of benchmark to really fairly compare methods. And for Jono, are there any methods to figure out which individual data is wrong or right instead of estimating whole data set accuracy? So this is also a very interesting question. So I think to figure, so this is actually related to model calibration. It is also related to uncertainty, also related to out of distribution detection. So I think there's existing solutions to individual data prediction. So so I think those areas I think are more sort of suitable to be used for this individual data prediction. All right, I think I've answered all the questions in the chat. Any other questions?
Liang, we have a question in person.
Okay.
Yeah, I had one question around the instance level versus like test set level idea that you just mentioned. I was curious if you've done studies of sort of if you evaluate using the instance, like one of the instance level methods, then compare it to the methods that you presented today. If there's any kind of difference there.
This is a very good question. So the insight we've got is that so the method that I presented today, so it's basically to predict your method on an overall test distribution. So if you do this on so the method I introduced, they probably can't do individual samples. Can't be effective for individual samples. So the problem is, so if you use, for example, image, for example, calibration methods or uncertainty-based methods, and they can give you some confidence levels for each individual sample. So this is the advantage. So the disadvantage is that if you add up these individual samples, they usually do not equal to the overall accuracy. So this is the problem. So usually this has sort of a small drift. So it could be consistently higher when you add each individual samples up. So the accuracy, overall accuracy you get is sort of higher or lower. So it's usually sort of not very accurate for the overall accuracy description. Besides, as I mentioned in the beginning of my slides, so if you use calibration methods to do this individual sample characterization, the problem is that calibration is still not very useful. Where is it? So okay. So calibration is not very useful for out of distribution data. So this is still an active area of research, how to make calibration methods work for out of distribution data.
Cool. Thank you.
Okay. Thanks.
I think that, is there any other question from people here? Okay, I think that's.
I think we're all good.
That's all. Okay, thanks a lot, Liang. I know it's also a really odd time for you, but thanks for this presentation. Hi, everyone. I just wanted to say a few remarks, trying to think about this tutorial. Thanks a lot for joining. And so the first part, in general, in this tutorial, we're trying to answer this really important question of how do we go from impressive performance on really well-controlled benchmarks to actually reliable performance in the wild, and what does that mean? How do we measure? How do we develop algorithms? So in the first part, there's like a gold standard attempt of trying to get good performance in the worst case over an appropriately defined set of perturbations. And this is really nice mathematically and gives us a framework to think about things. But we spoke about some computational and statistical challenges of this really, mathematical framework. And then we relax this a little bit to think about how do we evaluate beyond the worst case, given that worst case evaluation is really hard, we have all these challenges. And Ludwig presented about various kinds of thinking about distribution shifts. You could have benign or adversarial, natural or synthetic. And the answer is not easy. There's no one single explanation for how things work. And it's really very nuanced in terms of which things work well under what conditions. So two kind of highlighting factors seem to be that robustness interventions, especially through the worst case formulations that we had earlier, they don't always generalize, but they generalize to some extent. So in some cases, you do see improvements from these careful perturbations or this kind of worst case setup, but not always. And one thing that seems to be consistent across benign, adversarial, natural, synthetic, etc., is that generally training on more data provides consistent gains. So this was sort of the takeaway from stepping aside from worst case evaluations and thinking more broadly about distribution shifts that could occur. And then we made the problem even less hard so that, okay, let's even assume that we have some data. I mean, we don't even care about performance. We just want to evaluate how well it does. And so we have some data set of some distribution shift, and we want to see how well the model does. Like that, at least we should know so that we at least can measure whether we can deploy the system in the wild. And Liang spoke about a bunch of different promising directions, like where we could try to measure the distribution shift in some way via the data sets, or we could construct different self-supervised tasks that somehow are correlated with the task we care about. And so it gives you a signal on how well you would do. And you could also try to interpret the model's confidence carefully to get some signal on what exactly the performance would be on a distribution shift. So kind of going forward are the new directions, and what I see as unifying threads across all of these things is, yes, guarantees are important, we don't like them, but they're hard. And in general, all of these different, one common thing we see is that it's really hard to get or characterize performance once we think about distribution shifts. And so we need to figure out what's the right formalism or the language to reason about this. So, if, for example, in terms of the worst case setting, what exactly is the set of distributions we should think about? And similarly, for constructing more empirical evaluations, what are the set of distributions we should measure on? Or how do we think about the data set similarity in order to get unsupervised evaluation? So another effect that a lot of people were asking about as well is, how do we understand the effect of scale? Yes, we are in a situation where more data, bigger models are achieving impressive results, not just in this room here, but possibly in all the rooms in this workshops, right? And that leaves us with the open question of what are the problems that more data is not going to solve? What are we supposed to be working on under robustness? Right? And that's something we don't really understand. Do we need any new interventions, or do we just wait for scale to solve everything? And finally, I think, an elephant in the room is that it is kind of impossible to get a domain agnostic general purpose system that just always works across any shifts. And we do need to think about what's the appropriate domain knowledge or human input, or the setting that we are thinking about. And it seems indispensable to understand reliable performance. And so one other thing that we can think about is, how do we incorporate this domain knowledge more efficiently? And that kind of ties into the first part, is how do we bring that back in the language of what are the shifts and how do we get good performance from these models that reflect what exactly we care about in practice. And with that, I want to thank everyone, and thanks to my co-organizers, Ludwig, Liang, and Weijian, who couldn't unfortunately join us for the presentation, but was helping us with the tutorial throughout. Yeah, thanks everyone.